somewhere in the constellation Sagittarius, roughly 7,200 light-years from where you are right now, a star is dying in one of the most beautiful and terrifying ways the universe allows. It is not collapsing quietly. It is not fading into the dark the way most stars eventually will. Instead, it is exhaling its own body into space, sculpting its breath into a shape that has haunted astronomers since the day they first resolved it through their telescopes. An hourglass, a cosmic hourglass made of nitrogen-rich gas and luminous dust, glowing faintly in the infrared, stretching across a volume of space large enough to swallow our entire solar system several times over. It is as if the universe itself were keeping time, and the clock is running out. The star is called HD 168,625. It does not carry a poetic name. It does not appear in any ancient mythology or navigational chart. It is not visible to the naked eye. Most people, even most amateur astronomers, have never heard of it. But among the astrophysicists who study the most massive and unstable stars in our galaxy, this object commands a very particular kind of respect. It is a star that should not look the way it looks. It is a star that has already thrown off enormous quantities of its own processed nuclear material, roughly 1 to 2 times the entire mass of our Sun, carving a nebula shaped like an hourglass around itself. And the reason that shape matters, the reason it has kept research teams working late into the night and publishing urgent papers for decades, is because the last time we saw a star behave this way, shaping its expelled material into this precise geometry with this precise chemistry, the result was the most famous supernova of the 20th century. That supernova was called SN 1987A. It appeared in the Large Magellanic Cloud, a small companion galaxy to the Milky Way, on February 23, 1987. For months afterward, it was visible to the naked eye from the southern hemisphere, a pinpoint of new light where none had been before, marking the spot where a star had torn itself apart in an instant of unimaginable violence. The star that exploded, a blue supergiant named Sandulek -69°202, had been surrounded by an hourglass-shaped nebula strikingly similar to the one we now observe around HD 168,625. The resemblance between these two stars is not vague. It is not the kind of similarity that requires imagination or generous interpretation. It is structural, it is chemical, it is geometric. It is, in the measured language of astrophysical journals, disturbingly precise. And it raises a question that no one on Earth can yet answer with certainty. Is HD 168,625 about to explode? We do not know when. That is the honest answer, and it is also the deeply unsettling one. It could be tomorrow. It could be in 10,000 years. It could be in 100,000 years. The uncertainty is not a failure of science or a gap in our technology. It is a fundamental limitation imposed by the opacity of stellar matter. We cannot see the core of this star. We cannot directly measure the nuclear reactions burning at its center. We can only observe the surface, the wind, the nebula, and attempt to read the signs written there. And the signs, for those who know how to read them, are ominous. If it does explode, and it will explode eventually, because every star above a certain mass threshold ends its life this way, it will produce a supernova visible from Earth in broad daylight. For weeks, perhaps months, it will outshine every other star in the night sky. It will cast faint shadows on the ground at midnight. It will be the brightest stellar explosion witnessed by human beings in more than 4 centuries, since Kepler observed his supernova in 1604. And for those weeks, it will remind every person who looks up at a changed sky that the universe is not a painting hung on a wall. It is not a static backdrop to human affairs. It is a living, violent, constantly transforming engine of creation and destruction. And we are inside it. We are part of it. We are made from the debris of stars that died exactly this way long before our world existed. By the end of tonight, you're going to understand what makes this star so dangerous, why its hourglass nebula is a warning sign written in light and nitrogen, and what its eventual death will mean for our understanding of how the most massive stars in the universe come apart. You are going to learn about luminous blue variables, the rarest and most unstable class of stars known to science, objects so extreme that fewer than 50 of them are confirmed in the entire Milky Way galaxy, and its 400 billion stars. You are going to see how the shape of a nebula can encode the history of a star's past eruptions and forecast the nature of its future catastrophe. And you are going to confront a truth that most people never take the time to consider, a truth that is simultaneously humbling and strangely beautiful. The stars we see in the sky are not permanent fixtures. They are not eternal lanterns. They are processes. They are ongoing nuclear reactions, temporarily balanced, inevitably doomed. And some of those processes are nearing their end right now, at this very moment, as the ancient light from their surfaces crosses the empty reaches of the galaxy toward our waiting eyes and eager instruments. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To understand what is happening to HD 168,625, we first need to understand what kind of star it is. And to understand that, we need to talk about mass. Not weight, not size, not brightness, mass, because in the life of a star, mass is destiny. Mass determines how hot the core will burn, how long the star will live, what elements it will forge in its nuclear furnace, how it will lose its outer layers, and ultimately how it will die. A star's mass is its biography, written at birth, unalterable by any force in the universe, and final in its consequences. Everything that follows, every phase of evolution, every eruption, every transformation, is simply the working out of that initial condition through the relentless and impartial logic of physics. Our Sun has a mass of roughly 2 nonillion kilograms. That is a 2 followed by 30 zeros. It is an amount of matter so vast that no analogy truly captures it, but we can try. The Sun contains 99.86% of all the mass in the entire solar system. Jupiter, the largest planet, which could fit more than 1,000 Earths inside it, contains less than 1/10 of 1% of the Sun's mass. The Sun dominates everything around it, and yet it is ordinary. It is a middle-aged, medium-sized yellow dwarf star, one of billions of similar stars in the Milky Way. This mass is compressed by gravity into a sphere approximately 864,000 miles across, roughly 109 times the diameter of Earth. If you could hollow out the Sun, you would need approximately 1.3 million Earths to fill the cavity. Every second, the Sun converts approximately 620 million metric tons of hydrogen into approximately 615.7 million metric tons of helium through thermonuclear fusion at its core, where temperatures reach about 15 million Kelvin and the density exceeds 150 grams per cubic centimeter. The missing 4.3 million metric tons of matter per second do not vanish. They are transformed into energy, which radiates outward in all directions as photons, at a total power output of roughly 383 trillion watts. That is the luminosity of our star, one ordinary sun. The star that warms your face on a spring morning from 93 million miles away. Now consider this. HD 168,625 is not an ordinary star. Its mass is estimated at somewhere between 25 and 40 times the mass of our Sun. Its luminosity, the total energy it radiates per second in all directions, is roughly 300,000 times that of the Sun. 300,000 suns. If you gathered 300,000 perfect copies of our Sun and combined their total energy output into a single blazing point, you would approximate the radiance of this one star. If you replaced our Sun with HD 168,625, placing it at the center of the solar system, the inner planets would be obliterated. Mercury, Venus, Earth and Mars would be engulfed or incinerated. The habitable zone, that narrow orbital region where liquid water can exist on a planetary surface, would be pushed far beyond the orbit of Jupiter, perhaps past Saturn, into the cold outer reaches of the solar system. Life as we know it would never have arisen in such a system. The conditions that made Earth hospitable would not exist. Here is a scaled comparison to make this tangible. If our Sun were a single candle flame, gentle and warm, placed on a nightstand beside a bed, then HD 168,625 would be a roaring industrial furnace the size of an apartment building, radiating heat so intense that nothing could survive within a mile of its walls. One candle versus an industrial blaze. That is the difference between our star and this one. Both are powered by the same process, nuclear fusion, but the difference in mass creates a difference in output that is almost beyond comprehension. The star sits in the constellation Sagittarius, in the direction of the galactic center. When we look towards Sagittarius from Earth, we gaze along the thick plain of the Milky Way, through dense fields of stars, through gas clouds lit by hot young stellar clusters, through dark lanes of dust that block the visible light from more distant objects. HD 168,625 is located at a distance of approximately 2.2 kiloparsecs from Earth. 1 parsec equals roughly 3.26 light-years, so 2.2 kiloparsecs translates to about 7,200 light-years. The light we observe from this star today left its surface approximately 7,200 years ago. Those photons departed around 5,200 years before the Common Era. The Great Pyramid of Giza would not be built for another 2,700 years. The earliest known writing, Sumerian cuneiform, was still centuries in the future. Human civilization was a patchwork of small agricultural communities scattered across the fertile crescents and river valleys of the ancient world. And while those communities planted crops and shaped clay and told stories around fires, photons from this distant blue giant were already racing across the galaxy at 300,000 kilometers per second, crossing the vast emptiness between star systems, headed toward instruments that would not be invented for millennia. The determination of this distance is itself a triumph of careful, incremental science. For nearby stars, distances can be measured by parallax, the apparent shift in a star's position against the background sky as Earth orbits the Sun. The European Space Agency's Hipparcos satellite, launched in 1989, measured parallaxes for over 100,000 stars with milli-arcsecond precision. Its successor, Gaia, launched in 2013, extended these measurements to over 1 billion stars with micro-arcsecond accuracy for the brightest among them. For HD 168,625, however, the parallax is tiny, corresponding to a distance at the outer edge of reliable parallax measurement. The estimated distance of 2.2 kiloparsecs, or 7,200 light-years, is based on a combination of parallax measurements, spectroscopic estimates derived from the star's luminosity class and spectral type, and kinematic estimates using the star's radial velocity and proper motion in the context of galactic rotation models. Each method carries its own systematic uncertainties, and the convergence of multiple independent estimates on a consistent distance is what gives astronomers confidence in the value. The uncertainty in distance propagates directly into uncertainties in luminosity. Since the apparent brightness of a star depends on the square of the distance, meaning that a 10% error in distance corresponds to a roughly 20% error in luminosity. Getting the distance right matters enormously. How far is 7,200 light-years in terms we can feel? Here is another comparison. If you could drive a car continuously at 100 kilometers per hour, never stopping, never sleeping, never refueling, it would take approximately 78 billion years to reach this star. The universe is only 13.8 billion years old, so you could begin driving at the very instant of the Big Bang, and you would have completed less than 1/5 of the journey by now. You would still have 64 billion years of driving ahead of you. The distances between stars are not merely large. They are, by any human measure, essentially infinite. We cross them only with light and mathematics. But in galactic terms, 7,200 light-years is practically next door. The Milky Way spans roughly 100,000 light-years in diameter. It contains approximately 400 billion stars. Our Sun orbits the galactic center at a distance of about 27,000 light-years. HD 168,625 is embedded in the same galactic disk, orbiting the same core, part of the same slowly rotating structure of gas and dust and stars. When it eventually explodes, the supernova will be visible to the naked eye, one of the most spectacular astronomical events in the history of recorded observation. To appreciate the significance of this star, we need to understand the rare class it belongs to. HD 168,625 is classified as a luminous blue variable, abbreviated LBV. The term was introduced by the astronomer Peter Conti in 1984, building on decades of observational work by researchers including Roberta Humphreys and Chris Davidson at the University of Minnesota. LBVs are among the rarest stars known. They are massive, typically exceeding 25 solar masses. They are luminous, often surpassing 100,000 solar luminosities. They are hot, with surface temperatures ranging from about 8,000 to 25,000 Kelvin. And they are unstable, prone to irregular eruptions that can dramatically increase their brightness, change their spectral characteristics, and drive enormous quantities of material into space. The fundamental physics behind this instability involves the Hertzsprung-Russell diagram, the most important chart in stellar astrophysics, developed independently by the Danish astronomer Ejnar Hertzsprung around 1905 and the American astronomer Henry Norris Russell around 1913. This diagram plots stars according to two properties. The horizontal axis shows surface temperature, with hot blue stars on the left and cool red stars on the right. The vertical axis shows luminosity, with dim stars at the bottom and brilliant stars at the top. Most stars, including our Sun, fall along a diagonal band called the main sequence, where they spend the majority of their lives fusing hydrogen into helium in stable equilibrium. LBVs have departed the main sequence. They have evolved into the upper reaches of the diagram, approaching a critical boundary known as the Humphreys-Davidson limit. This empirical boundary, identified by Humphreys and Davidson in 1979, represents the maximum luminosity at which a star can remain stable. Beyond this limit, the outward pressure of the star's own radiation begins to exceed the gravitational force holding the star together. Photons, streaming outward from the nuclear furnace in the core, push against the atoms in the star's atmosphere with enough force to accelerate them to escape velocity. The star bleeds matter into space, not gently, not slowly, but in powerful winds and catastrophic eruptions that can strip solar masses of material in centuries or less. The Humphreys-Davidson limit is not a sharp line but a broad zone, and its exact position depends on the star's temperature, composition, and evolutionary history. At higher temperatures, the limit occurs at higher luminosities. At lower temperatures, where the atmosphere is cooler and more opaque, the limit drops. The result is a boundary in the Hertzsprung-Russell diagram that slopes from upper left to lower right, forming an envelope beyond which no stable stars are found. Stars that evolve toward this boundary from the main sequence encounter it like a wall. They cannot pass through it in steady state. Instead, they oscillate near the boundary, shedding mass in episodic outbursts that reduce their luminosity temporarily, only to recover and approach the limit again. This back-and-forth behavior, a kind of self-regulating dance between luminosity and mass loss, is one of the defining characteristics of the LBV phase and is thought to continue until the star has shed enough mass to move away from the instability strip, or until it evolves rapidly toward core collapse. HD 168,625 sits near this limit. Its spectral classification is B6ia, indicating a hot blue supergiant of the highest luminosity class. Its surface temperature lies in the range of 12,000 to 15,000 Kelvin, roughly twice the temperature of the Sun's surface. At this temperature, the star radiates most of its energy in the ultraviolet, invisible to our eyes but detectable by space-based observatories. Its powerful stellar wind drives mass outward at roughly 200 kilometers per second, stripping material from the surface at a rate of approximately 100,000th of a solar mass per year. The most famous luminous blue variable in our galaxy is Eta Carinae, a massive binary system located roughly 7,500 light-years from Earth. Eta Carinae erupted spectacularly in 1843, briefly becoming the second brightest star in the sky despite its enormous distance. During that eruption, it expelled 10 to 40 solar masses of material, forming the Homunculus Nebula, a bipolar hourglass-shaped structure, strikingly similar to the nebula around HD 168,625. Both show two lobes separated by a pinched equatorial waist. Both contain nitrogen-enriched gas. This recurring hourglass geometry is not coincidence. It is a physical signature of how the most massive stars shed their outer layers when rotation and radiation pressure conspire to channel the outflow preferentially along the poles. The Great Eruption of Eta Carinae, as it is now called, remains one of the most extraordinary events in the recorded history of stellar astronomy. The star expelled more mass in a few years than most stars lose in their entire lifetimes, and the mechanism that drove the eruption is still debated. Some researchers have proposed that it was triggered by a close passage of the binary companion, which plunged through the outer atmosphere of the primary star and ejected material through hydrodynamic drag. Others have suggested a radiation-driven super-Eddington wind, amplified by the interaction of the binary components. Still others have invoked deep-seated explosive events, perhaps related to instabilities in the stellar envelope that propagated outward as shock waves. The diversity of proposed mechanisms reflects the depth of our ignorance about the most extreme episodes of stellar mass loss. Here is a third comparison to anchor the rarity. Among the roughly 400 billion stars in the Milky Way, fewer than 50 are confirmed luminous blue variables. If every grain of sand on every beach on Earth, roughly 7.5 quintillion grains, represented about 53 stars, then all the LBVs in the galaxy would be represented by fewer than 50 grains scattered across all the beaches on the planet. Finding one would be like searching every coastline, every desert, every riverbed for a specific unmarked grain. That is how rare these objects are, and HD 168,625 is one of them. The history of LBV recognition stretches back further than the name itself. One of the earliest known luminous blue variables is P Cygni, a star in the constellation Cygnus that appeared as a new star in 1600, startling European astronomers who observed it brighten to third magnitude before fading, and then brightening again over subsequent decades. P Cygni's spectrum became the archetype for a particular kind of spectral line profile, the P Cygni profile, characterized by a blue-shifted absorption component adjacent to a red-shifted emission component, indicating a powerful outflowing wind. This profile is now recognized as a hallmark of massive stars with dense, fast-moving stellar winds, and it is seen in the spectrum of HD 168,625 as well. Another instructive example is AG Carinae, located roughly 20,000 light-years from Earth, which has been observed to vary by more than a full magnitude in brightness over timescales of years to decades. AG Carinae is surrounded by a ring nebula roughly 1.2 parsecs in diameter, composed of material ejected during past eruptions. Detailed studies of this nebula have revealed nitrogen enrichment and dust formation patterns strikingly similar to those observed in the Hourglass around HD 168,625, suggesting that the physical mechanisms driving mass ejection in LBVs are broadly similar across the class, even when the resulting nebular morphologies differ. Then there is S. Doradus, the prototype of the class in the Large Magellanic Cloud, whose variations in brightness were first systematically documented in the 1960s. S. Doradus undergoes slow oscillations in temperature and radius, expanding and cooling during bright phases, while contracting and heating during faint phases, maintaining roughly constant luminosity throughout. This behavior, called S. Doradus variability, is believed to reflect changes in the opacity and structure of the star's outer atmosphere, rather than changes in the total energy output from the core. These examples illustrate a crucial principle. LBVs are not simply very bright stars, they are stars in crisis. The physics of the crisis centres on the Eddington luminosity, named for the British astrophysicist Sir Arthur Eddington, who first described it in the 1920s. The Eddington luminosity is the maximum luminosity at which a star can remain in hydrostatic equilibrium, meaning the outward force of radiation pressure exactly balances the inward pull of gravity. For a star composed primarily of ionized hydrogen, the Eddington luminosity depends only on the star's mass. A star with 30 solar masses has an Eddington luminosity of roughly 1 million solar luminosities. Stars approaching this limit are in a precarious state. Any increase in luminosity, any decrease in mass, any change in the opacity of the outer layers that increases the coupling between radiation and matter can push the star over the edge. When that happens, radiation drives matter outward faster than gravity can hold it. The star erupts. The Eddington limit, as classically defined, assumes a spherically symmetric, fully ionized, pure hydrogen atmosphere. Real stars are more complicated. They have layers of partially ionized material, particularly iron, which has a complex electron shell structure and thousands of spectral lines that can absorb photons. In these partially ionized regions, the opacity of the material, its resistance to the passage of radiation, can spike dramatically. This creates a situation called the opacity-modified Eddington limit, or sometimes the iron opacity bump, where the effective Eddington limit is reached locally in certain layers, even when the total luminosity of the star is safely below the classical Eddington limit. The result is that instabilities can develop in subsurface layers, driving convective turbulence, atmospheric inflation, and episodic mass ejections without the total luminosity ever formally exceeding the classical threshold. This modified understanding of the Eddington limit has been critical to explaining LBV behavior and is one of the key insights of the past 2 decades of massive star research. The theory of radiation-driven stellar winds, first formalized in a landmark paper by Castor, Abbott, and Klein in 1975, often abbreviated as CAK theory, describes how photons from the star's interior transfer momentum to atoms in the atmosphere through the absorption of light at spectral line frequencies. Each absorbed photon delivers a tiny kick to the absorbing atom. In a massive, luminous star, the sheer number of photons is so enormous that the cumulative effect of these tiny kicks is sufficient to accelerate atmospheric material to escape velocity. The wind speed and mass loss rate predicted by CK theory depend on the luminosity, mass, surface temperature, and chemical composition of the star, particularly the abundance of iron group elements that provide most of the spectral lines. For HD 168,625, the steady wind carries away roughly 100,000th of a solar mass per year, a river of plasma streaming outward at 200 kilometers per second, filling the space around the star with a slowly expanding cocoon of hot gas. Over the star's remaining lifetime, this wind alone will strip away several solar masses of material. But the wind is only the baseline. The eruptions that created the Hourglass Nebula involved mass loss rates, orders of magnitude, higher, far exceeding anything the steady wind mechanism can explain. These eruptive events remain among the most poorly understood phenomena in stellar physics. The circumstellar nebula is what makes this star truly alarming. Observations with the Hubble Space Telescope have resolved the hourglass structure in remarkable detail. The Spitzer Space Telescope provided infrared images showing thermal emission from warm dust in the nebula. Ground-based spectroscopy from the European Southern Observatory's Very Large Telescope revealed the chemical composition of the nebula gas. The total mass of the nebula is estimated at 1 to 2 solar masses. The expansion velocity of the gas is 40 to 60 kilometers per second. Based on these measurements, astronomers have calculated that the ejection event occurred between several thousand and roughly 10,000 years ago. In cosmic terms, this is almost impossibly recent. Within the span of human civilization, this star convulsed violently enough to throw an entire sun's worth of material into space. The chemistry of the nebula tells us something further. The gas is enriched in nitrogen and depleted in carbon and oxygen. This is the unmistakable signature of CNO cycle processing, the nuclear pathway by which massive stellar cores convert hydrogen to helium using carbon, nitrogen, and oxygen isotopes as catalysts. When CNO-processed material appears in the nebula, it means the star's deep interior has been exposed. Material that was once buried thousands of kilometers below the surface has been dredged up by convection or uncovered by mass loss. The star is showing us its insides, and what it is showing us is a star in an advanced state of evolution, far beyond the main sequence, deep into the sequence of nuclear burning stages that will eventually end in a core of iron and a catastrophic collapse. And this brings us to the central question that defines the study of HD 168,625. The last time astronomers saw a star with this specific combination of properties, this mass, this luminosity, this temperature, this nitrogen enrichment, this hourglass nebula, that star was Sandu Lake negative 69 degrees 202. It exploded as SN 1987A, the closest observed supernova in nearly 4 centuries. Nathan Smith and his colleagues have documented the resemblance in peer-reviewed publications, arguing that HD 168625 may be a galactic twin of the SN 1987A progenitor, a star at the same evolutionary stage, on the same trajectory, heading toward the same violent end. We may be watching the next great supernova as it prepares to happen. But the problem is profound and irreducible. We cannot see the core. We cannot measure when the final moment will come. We can only watch and measure and wonder. And what the measurements tell us is deeply troubling. The core of a massive star is a place of almost inconceivable violence. No human instrument has ever observed one directly. No probe will ever descend into one. Even light itself cannot escape from the deep interior, trapped by the sheer density of matter that surrounds the nuclear furnace. Everything we know about stellar cores comes from mathematical models, from the equations of nuclear physics and thermodynamics, applied with painstaking care over decades of computational effort. But even without direct observation, what those models describe is breathtaking in its ferocity. To understand what is happening inside HD 168625, we need to journey inward, past the photosphere where light escapes into space, past the radiative zone where energy is transported by photons bouncing endlessly between atoms, past the convective envelope where superheated plasma churns and rolls, in vast turbulent cells like water in a boiling pot, and deeper still, through layer after layer of increasingly dense and hot material, until we reach the center. There, compressed by the gravitational weight of everything above it, the core burns at temperatures exceeding 100 million Kelvin. The density reaches values thousands of times greater than any material found naturally on Earth. Under these conditions, atomic nuclei are stripped bare, and the positive charge repelling them from one another is overcome by the thermal energy of their motion. They collide and fuse, and in fusing, they release energy. This energy, radiating outward, is the only thing standing between the star and gravitational collapse. The star is a battleground. Gravity pulls inward, relentlessly and without pause. Nuclear energy pushes outward. As long as the core can generate enough energy through fusion, the star survives. When it cannot, the star dies. A star like our Sun will spend roughly 10 billion years on the main sequence, steadily converting hydrogen into helium at a measured pace. It is a slow, patient, almost leisurely process. Our Sun is about 4.6 billion years old and is roughly halfway through its hydrogen-burning life. It will continue in this state for another 5 billion years before it begins to change. But a star with 25 to 40 solar masses does not have that luxury. The more massive a star is, the greater the gravitational pressure on its core, and the hotter the core must burn to resist that pressure. The hotter the core burns, the faster it consumes its fuel. The relationship between mass and lifetime is steep and unforgiving. A star with 10 times the Sun's mass does not live 1/10 as long. It lives roughly 1,000th as long. A star with 30 solar masses might spend only 6 to 8 million years on the main sequence. Compare that to the Sun's 10 billion. It burns through its hydrogen with breathtaking speed, driven by the enormous pressure at its center. The luminosity-mass relationship explains this cruel arithmetic. A star's luminosity scales roughly as the cube or even the fourth power of its mass, while the total fuel supply scales only linearly with mass. Double the mass, and you roughly double the fuel, but you increase the burn rate by a factor of 8 to 16. The net effect is that the lifetime scales inversely, with roughly the square or cube of the mass. A star 50 times more massive than the Sun is not 50 times shorter-lived. It is tens of thousands of times shorter-lived. This is why massive stars are rare in the sky, despite being formed in reasonable numbers. They burn so fast that they are gone almost as soon as they appear, relative to cosmic timescales. The Milky Way has been forming stars for over 13 billion years, and yet virtually every massive star ever born in our galaxy has already died. The ones we see now are the most recent generation, born only millions of years ago, already racing toward their ends. When the hydrogen in the core is exhausted, the star does not go dark. What happens instead is a sequence of events that accelerates with terrifying momentum. The core, no longer generating enough energy to resist gravity, contracts. As it contracts, it heats up. When the temperature reaches approximately 100 million Kelvin, a new set of nuclear reactions ignites. Helium nuclei, which have been accumulating as the ash of hydrogen burning, begin to fuse together, producing carbon and oxygen. This is core helium burning, and it sustains the star for a while, but not nearly as long as hydrogen burning. For a 30 solar mass star, core helium burning might last only a few 100,000 years, a fraction of the hydrogen burning phase. The fuel supply is smaller, and the energy yield per reaction is lower. The physics of helium burning deserve a moment of attention, because they involve one of the most remarkable coincidences in nuclear physics. The fusion of 3 helium nuclei into a single carbon nucleus, known as the triple alpha process, proceeds through an intermediate step. 2 helium nuclei first combine to form an unstable beryllium-8 nucleus, which decays back into 2 helium nuclei in about 1/10 trillionth of a second. For the triple alpha process to proceed, a 3rd helium nucleus must collide with the beryllium-8 during that fleeting interval. This would be vanishingly unlikely, except for a fortuitous property of the carbon-12 nucleus. It possesses an excited energy state, called the Hoyle state, after the astrophysicist Fred Hoyle, who predicted its existence in 1953, before it was experimentally confirmed, at exactly the right energy to create a resonance that dramatically enhances the reaction rate. Without this resonance, the triple alpha process would be inefficient. Very little carbon would be produced, and the entire chain of heavy element synthesis that depends on carbon as a building block would be broken. The Hoyle state is one of those narrow physical parameters on which the chemical richness of the universe depends. Its existence is a prerequisite for organic chemistry, for planets with carbon-based geology, and for life as we know it. Once the helium is exhausted and carbon burning begins, the star enters a qualitatively different regime. The temperatures required for each successive burning stage are higher, the energy released per reaction is lower, and the neutrino losses from the core become increasingly severe. During carbon burning, which occurs at temperatures of roughly 500 million to 1 billion Kelvin, the primary products are neon, sodium, and magnesium. The reactions also produce a cascade of gamma-ray photons and free neutrons, the latter of which can be captured by existing nuclei to build up heavier isotopes through the slow neutron capture process. The carbon-burning phase in a 30 solar mass star lasts roughly 1,000 years, a dramatic compression from the hundreds of thousands of years of helium burning that preceded it. But even this is leisurely compared to what follows. When the helium runs out, the pattern repeats. The core contracts, the temperature rises, carbon ignition begins, carbon nuclei fuse to produce neon, sodium, magnesium. This stage is shorter still, perhaps 1,000 years. Then neon burning ignites, consuming the neon produced in the previous stage. This lasts perhaps a year. Then oxygen burning, 6 months. Each stage is shorter, hotter, and more desperate than the last. The star is running through its fuel reserves with increasing franticness, each new source of energy smaller and less efficient than the one before. The brevity of these final stages is worth dwelling on because it is so counterintuitive. We are accustomed to thinking of stellar timescales as vast, measured in millions or billions of years, and for most of a star's life, this is true. But the final act is compressed into an absurdly brief interval. If the star's entire main sequence lifetime of 6 to 8 million years were represented by a single calendar year, then helium burning would occupy the last 2 weeks. Carbon burning would last about 4 seconds. Neon burning would be over in a few hundredths of a second. Oxygen burning would occupy a few thousandths of a second. And silicon burning, the final stage, would take less than 1/10,000th of a second. The star spends millions of years in steady hydrogen burning, and then races through all the remaining fuel in what amounts to a cosmic eye blink. The acceleration is driven by the relentless increase in neutrino losses at higher temperatures, which drain energy from the core faster than ever, forcing it to burn hotter and faster just to maintain the pressure needed to resist gravitational collapse. And then the final stage arrives, silicon burning, the fusion of silicon nuclei into iron. This last gasp of nuclear energy generation lasts approximately 1 day, 24 hours. After millions of years of patient hydrogen burning, after hundreds of thousands of years of helium burning, after thousands of years of carbon burning, after months and years of neon and oxygen burning, the final fuel is consumed in a single rotation of the Earth. And when silicon burning is complete, the core is made of iron. Iron is the end of the road. It is the most tightly bound nucleus in nature, meaning that fusing iron does not release energy. It requires energy. Every previous stage of nuclear burning released energy that could push outward against gravity. Iron fusion is endothermic. It absorbs energy. When the core becomes iron, the star has exhausted every possible source of nuclear fuel. There is nothing left to burn. Nothing left to push back against the immense weight pressing inward from every direction. The core collapses. But the transition from silicon burning to collapse is not as simple as running out of fuel and stopping, like a car sputtering to a halt on an empty tank. The physics of the final hours is considerably more dramatic and more complex. As the iron core grows, it is supported not primarily by thermal pressure, the heat of the gas pushing outward, but by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle. Electrons, being fermions, resist being compressed into the same quantum state. This resistance provides an additional source of pressure, independent of temperature, that can support the core even as thermal energy is increasingly radiated away by neutrinos. And neutrinos, during these final stages, become the dominant mechanism of energy loss. This is a critical and counterintuitive point. During the hydrogen burning phase, and even through helium burning, the energy produced in the core is carried outward primarily by photons, which bounce from atom to atom through the dense stellar interior, slowly diffusing outward over thousands or millions of years. But during the advanced burning stages, the temperatures become so extreme that a different process takes over. Pairs of neutrinos and antineutrinos are produced by the interaction of photons and electrons at temperatures exceeding roughly 1 billion Kelvin. Unlike photons, these neutrinos interact almost not at all with matter. They stream straight out of the star, carrying energy with them, leaving the core to cool, even as nuclear reactions continue to inject heat. The neutrino losses are catastrophic. During silicon burning, the neutrino luminosity of the star, the total power emitted in the form of neutrinos, exceeds the photon luminosity, the visible light output, by a factor of roughly 10,000. The star is radiating vast amounts of energy in a form that no telescope can see, draining its thermal reserves with shocking speed. This is why the late burning stages are so short. It is not merely that the fuel supply is smaller, it is that the energy is being stolen by neutrinos faster than fusion can replace it. The moment of collapse is triggered by one of two processes, or more likely a combination of both. The first is photodisintegration, the destruction of iron nuclei by extremely energetic photons. At temperatures exceeding about 10 billion Kelvin, the photons in the core are energetic enough to smash iron nuclei apart into individual protons, neutrons, and helium nuclei. This process absorbs an enormous amount of energy, roughly 170 billion electron volts per iron nucleus, draining the core of the thermal energy that was helping to support it. The second process is electron capture, in which protons in the iron nuclei absorb electrons and are converted into neutrons, emitting neutrinos in the process. This reduces the number of electrons in the core, which reduces the electron degeneracy pressure that was providing the primary mechanical support. Both processes operate simultaneously, each reinforcing the other, and together they initiate the catastrophic loss of pressure support that triggers the final collapse. The collapse, once it begins, is irreversible. There is no physical process that can halt it. The core goes from a roughly Earth-sized sphere to a city-sized ball of neutrons in less than 1 second. The gravitational potential energy released during this collapse is staggering. roughly 3 times 10 to the 46 joules, equivalent to the total energy output of the Sun over its entire 10 billion year lifetime, released in a fraction of a second. 99% of this energy escapes in the form of neutrinos. About 1% goes into the kinetic energy of the supernova ejector and the light of the explosion. That 1%, the tiny fraction that we can see, is still enough to briefly outshine an entire galaxy. The collapse happens in milliseconds. The iron core, roughly the size of Earth, but containing 1 to 2 solar masses of material, falls inward at speeds approaching 1/4 of the speed of light, 75,000 kilometers per second. In less than a second, the core compresses to a density comparable to an atomic nucleus, roughly 270 million metric tons per cubic centimeter. At this density, the core is essentially one giant nucleus, composed almost entirely of neutrons, packed so tightly that a teaspoon of the material would weigh approximately 5.5 billion metric tons. The infalling outer layers slam into this suddenly rigid, incompressible core and rebound violently. A shockwave propagates outward through the star, heated by neutrinos streaming out of the collapsing core at nearly the speed of light. The shockwave tears through the outer layers, accelerating them outward, heating them to billions of degrees. In a matter of hours, the star's outer envelope, everything above the collapsed core, is blown into space at velocities of tens of thousands of kilometers per second. This is a core collapse supernova. It is one of the most energetic events in the known universe, releasing roughly 10 to the 46 joules of energy in the form of light and kinetic energy, and roughly 100 times that much in the form of neutrinos. For a few weeks, the exploding star can outshine its entire host galaxy, a single point of light briefly rivaling the combined luminosity of hundreds of billions of stars. That is what awaits HD 168,625. That is the future written in its mass, its chemistry, and its hourglass nebula. But here is the problem. We do not know when this future will arrive. We cannot see the core. We cannot measure what nuclear fuel stage the star has reached. We cannot determine how much hydrogen remains, how far through the helium or carbon or oxygen burning the star has progressed, or how close the core is to producing that fatal accumulation of iron. We have theoretical models that describe the evolution of massive stars in impressive detail. We have computer simulations that can track the temperature, density, and composition of every layer from the center to the surface. But these models contain uncertainties, and the uncertainties are not trivial. They are fundamental. One of the deepest uncertainties involves mass loss. Massive stars shed material throughout their lives, through steady stellar winds, and through occasional dramatic eruptions. The rate of this mass loss profoundly influences the star's evolution. It determines how much mass remains at the moment of core collapse, which in turn determines the nature of the explosion. A star that retains most of its hydrogen envelope might produce a Type II plateau supernova, characterized by a sustained brightness plateau as the shock wave moves through the hydrogen-rich outer layers. A star that has lost most of its hydrogen might produce a Type Ib, or even a Type Ib supernova. A star that loses virtually all of its hydrogen and helium might produce a Type Ic. And at the extreme upper end, if the star retains so much mass that the collapsing core exceeds a critical threshold, it might collapse directly into a black hole with little or no visible explosion at all. It would simply vanish. Which of these fates awaits HD 168,625? We do not know. The Hourglass Nebula tells us that the star has already lost at least 1 to 2 solar masses through ejection events. Ongoing wind measurements indicate continued mass loss, but the total amount lost over the star's entire lifetime, and the amount it will lose between now and the moment of core collapse, remains deeply uncertain. The history of how this star was identified is itself a story of patient accumulation of knowledge across generations. HD 168,625 appears in the Henry Draper Catalogue, one of the most ambitious astronomical surveys ever undertaken. The catalogue was compiled at Harvard College Observatory beginning in the 1880s under the direction of Edward Charles Pickering. The actual work of classifying stellar spectra from thousands of photographic plates was carried out by a team of women astronomers. sometimes called the Harvard computers, including Williamina Fleming, Annie Jump Cannon, and Cecilia Payne-Gaposchkin. Cannon alone classified roughly 350,000 stars over her career, developing the spectral classification system that, with modifications, is still used today. When HD 168,625 received its catalogue designation, it was simply one entry among hundreds of thousands, its extraordinary nature completely hidden behind a modest apparent brightness and an unremarkable entry in a photographic plate. It was not until the latter half of the 20th century that the star's true character began to emerge. Infrared astronomy, which detects heat radiation invisible to the naked eye, matured dramatically in the 1970s and 1980s with the development of new detector technologies and the launch of infrared-sensitive space telescopes. The infrared astronomical satellite, known as IRIS, was launched in 1983 and conducted the first all-sky survey at infrared wavelengths. It revealed thousands of sources that were invisible in optical light, including circumstellar nebulae around massive stars. Observations in the 1980s and 1990s, using ground-based infrared instruments, began to reveal the dust shell surrounding HD 168,625. The star was embedded in a cocoon of warm material, glowing at wavelengths far beyond what the human eye can detect. Follow-up observations with the Hubble Space Telescope in the late 1990s provided the first clear images of the bipolar structure. The hourglass shape was unmistakable. Two lobes of emission, extending in opposite directions from the central star, separated by a denser equatorial structure. The resemblance to the homunculus nebula around Eta Carinae was immediately noted, as was the resemblance to the circumstellar nebula that had been mapped around SN 1987A after the explosion revealed its pre-existing structure. And it gets worse. The comparison to SN 1987A's progenitor is not a vague or impressionistic one. It is detailed and quantitative. In a landmark paper published in 2007, Nathan Smith conducted a careful comparative analysis of the two stars. He measured the luminosities. He compared the spectral types. He analyzed the chemical compositions of the nebulae. He measured the morphologies, the sizes, the expansion velocities. Point by point, the two objects matched. Both had luminosities in the range of a few 100,000 solar luminosities. Both had blue supergiant spectral types. Both had bipolar nebulae of similar dimensions. Both showed nitrogen enrichment consistent with cyanoprocessed material dredged up from the stellar interior. Smith concluded that HD 168,625 might be a galactic analogue of the SN 1987 A progenitor, a star in essentially the same evolutionary condition, heading toward the same ultimate fate. This conclusion resonated through the astrophysical community, because SN 1987A was already one of the most studied events in the history of astronomy. It was the first supernova visible to the naked eye since Kepler's supernova in 1604, nearly 400 years earlier. It was the first supernova from which neutrinos were detected, a handful of ghostly particles captured by detectors in Japan, the United States, and Russia, confirming the theoretical prediction that core collapse supernovae produce immense bursts of neutrinos that carry away most of the gravitational energy. The detection of those neutrinos was a triumph of theoretical astrophysics and experimental particle physics, and it earned Masatoshi Koshiba a share of the Nobel Prize in Physics in 2002. But SN 1987A also posed a problem that shook the foundations of stellar evolution theory. Before it exploded, its progenitor was a blue supergiant. This was unexpected. The standard theoretical models of the time predicted that massive stars should explode as red supergiants, swollen and cool, with radii hundreds of times that of the Sun. The fact that Sander Lake -69 degrees 202 was blue and relatively compact when it exploded forced a major revision in the understanding of stellar evolution. Some massive stars, it turned out, undergo a complex evolutionary path. They leave the main sequence, expand into red supergiants, and then evolve back toward higher temperatures, becoming blue supergiants again before they explode. The Hourglass Nebula was material shed during this journey. sculpted by subsequent phases of mass loss and stellar wind interaction. If HD 168,625 is on the same evolutionary track, it too may have passed through a red supergiant phase in its past. It may have swollen to enormous size, hundreds of times the Sun's radius, with a cool surface temperature of only 3,000 to 4,000 Kelvin. During that phase, it would have lost mass through a slow, dense wind, forming a shell of material around itself. Then, as internal processes shifted the star's structure, it contracted and heated, evolving back to its current blue supergiant state. The powerful, fast wind of the blue supergiant phase would have swept into the slow, dense red supergiant wind, compressing it, shaping it, sculpting it into the hourglass structure we observe today. This scenario, known as the interacting stellar winds model, provides a natural explanation for the bipolar morphology. The equatorial density enhancement, left over from the red supergiant phase when mass loss was concentrated in the equatorial plane, acts as a barrier. The fast blue supergiant wind, encountering less resistance at the poles, punches through preferentially in those directions, inflating the two lobes of the hourglass. This evolutionary pathway, sometimes called a blue loop on the Hertzsprung-Russell diagram, is predicted by some stellar evolution models, but remains poorly understood. The details depend sensitively on multiple factors: the initial mass of the star, the metallicity, meaning the fraction of elements heavier than helium, which affects opacity, and therefore how radiation is transported through the star, the rate of mass loss at different evolutionary phases, the efficiency of convective mixing, which transport material and energy between different zones of the stellar interior. Different models, using different assumptions about these factors, produce different predictions. Some predict blue loops, others do not. The specific conditions that cause a star to evolve back from a red supergiant to a blue supergiant remain a subject of active research and debate. Rotation adds another layer of complexity that current models struggle to handle. Massive stars often rotate rapidly, sometimes at significant fractions of their critical rotation rate, the speed at which centrifugal force at the equator would equal gravitational force. Rotation affects the star's structure by introducing centrifugal support, which makes the star oblate. It affects internal mixing by generating circulation currents that can transport processed material from the core toward the surface. It affects mass loss by enhancing the stellar wind at the equator, where the effective gravity is reduced. And it affects the star's evolution by changing the relationship between temperature and luminosity at each evolutionary phase. A rapidly rotating star follows a different evolutionary track than a slowly rotating one with the same mass, and the rotation rate of HD 168,625 is not precisely known. The hourglass shape of the nebula may itself be a clue about the star's rotation. Bipolar nebulae, with two lobes and a pinched equatorial waist, are commonly associated with stars that have experienced asymmetric mass loss, with more material concentrated in the equatorial plane. This equatorial enhancement can arise from rapid rotation, which enhances the stellar wind at the equator, or from the presence of a binary companion whose gravitational influence can channel the outflow into a disk or torus. No companion to HD 168,625 has been definitively confirmed, despite searches using high-resolution spectroscopy and interferometry. But the absence of evidence is not evidence of absence. Close binary companions can be difficult to detect, especially when one star is far more luminous than the other, drowning out the companion's light. The chemical fingerprints in the nebula provide yet more evidence of extreme evolution. The elevated nitrogen and reduced carbon and oxygen abundances are characteristic of material that has been processed through the CNO cycle, the dominant hydrogen burning pathway in massive stellar cores. In the CNO cycle, carbon, nitrogen and oxygen nuclei serve as catalysts, being transformed into each other as they participate in a chain of fusion reactions that ultimately converts 4 hydrogen nuclei into 1 helium nucleus. The equilibrium state of the cycle produces a characteristic abundance pattern, with nitrogen enhanced at the expense of carbon and oxygen. When this pattern appears at the stellar surface or in the surrounding nebula, it is a definitive sign that material from the deep interior, where the CNO cycle operates, has been brought to the surface. The star is revealing its processed innards, and those innards tell us that nuclear burning has been proceeding for a long time and has substantially altered the star's internal chemistry. But here's what makes this truly terrifying. All of the observational evidence, the luminosity, the temperature, the spectral type, the nitrogen enrichment, the Hourglass nebula, the kinematic similarity to the SN 1987A progenitor, points toward a single conclusion. This star is in the late stages of its life. It has left the main sequence far behind. It has processed much of its core hydrogen and possibly its core helium. It may be in one of the advanced burning stages, carbon or neon or oxygen or even silicon, at this very moment, and we have no way to know. The core is opaque. The surface reveals only indirect clues. The models disagree on the details, and the star, indifferent to our curiosity and our anxiety, continues to burn. The disconnect between surface and core is one of the most frustrating aspects of massive star astrophysics. During the final burning stages, the core evolves on timescales of years, months, and ultimately hours, while the surface, insulated by the vast mass of the overlying layers, may show little or no response. A star could be in its final day of silicon burning, less than 24 hours from catastrophic collapse, and appear essentially unchanged to an observer. The photosphere would shine with nearly the same temperature and luminosity as it did a century earlier. The spectral lines would show the same wind velocity, the same chemical abundances. The star would look perfectly normal, and then, with no visible warning, it would vanish. There are theoretical predictions of subtle pre-supernova indicators, effects that might betray the approach of the end to an observer with sufficiently sensitive instruments. Some models suggest that the intense neutrino emission during the late burning stages could deposit a small amount of energy in the outer layers of the star, causing them to expand slightly and the surface to cool by a few hundred Kelvin in the final years before collapse. This has been called the pre-supernova neutrino brightening, and it would manifest as a subtle reddening and dimming of the star in optical light, accompanied by a slight brightening in the infrared. The effect is predicted to be small, perhaps a few tenths of a magnitude, and would be difficult to distinguish from the normal variability of a massive supergiant. Other models predict that convective instabilities in the oxygen and silicon burning shells could generate waves that propagate outward, causing the stellar surface to pulsate with increasing intensity in the final weeks or months. These pulsations might be detectable as rapid, irregular brightness variations, a kind of stellar tremor that signals the approaching catastrophe. Whether any of these predicted signatures are real, and whether they are detectable at a distance of 7,200 light-years, remains an open question. What is certain is that we have never observed them, because we have never been watching a massive star with modern instruments at the moment it exploded. Every supernova we have observed has been in a distant galaxy, too far for detailed pre-explosion monitoring of the progenitor. The galactic supernovae of the past, Kepler's star, Tycho's star, the Crab Nebula's progenitor, all occurred before the invention of modern telescopes. We are, in a profound sense, still waiting for our first real-time observation of a massive star's final moments. HD 168,625 may eventually provide that opportunity, but it may not provide it in our lifetimes, or in the lifetimes of our great-grandchildren, or in the lifetimes of their descendants for 1,000 generations. Astronomers have approached the puzzle of HD 168,625 from multiple angles over the past several decades, each method illuminating a different facet of this extraordinary star, and each ultimately running into its own walls of limitation. Understanding these approaches, their insights, and their failures is essential to grasping the full depth of the mystery and the profound difficulty of predicting the death of a star we can see, but can never truly know. The first and most fundamental approach has been systematic photometric monitoring, the careful repeated measurement of the star's brightness over time. For luminous blue variables, brightness variations are the defining characteristic. A confirmed LBV undergoes irregular fluctuations of 1 to 2 magnitudes, brightening and dimming over timescales of months to years. These variations signal active instability, episodes during which the star's outer layers expand and cool, then contract and heat, sometimes gradually and sometimes violently. Monitoring these changes provides a window into the star's current state of stability or instability. Photometric monitoring of HD 168,625 has been carried out over several decades using both ground-based telescopes and space-based instruments like the Hipparcos satellite, which operated from 1989 to 1993, and catalogued the positions, parallaxes, and brightnesses of over 100,000 stars with unprecedented precision. The results have been frustratingly ambiguous. Some studies have reported small amplitude brightness variations, on the order of a few tenths of a magnitude, that could be consistent with low-level LBV activity, or with the pulsations expected in massive blue supergiants. Others have found the star to be relatively stable during the periods observed. The difficulty is one of timescale. LBV eruptions can be separated by decades or even centuries of quiescence. A star that appears stable during a 30-year monitoring campaign might erupt spectacularly a year after the observations stop. We are trying to observe a process that unfolds on timescales much longer than a typical human career, and the snapshot we have may not represent the full range of the star's behavior. This ambiguity has led to the classification of HD 168,625 as an LBV candidate rather than a confirmed LBV. The distinction matters. A confirmed LBV has been directly observed undergoing the characteristic brightness variations. A candidate shows many of the hallmarks of the class: the luminosity, the spectral type, the circumstellar nebula, the chemical enrichment, but has not been caught in the act of erupting. This could mean the star is in a quiescent phase between eruptions. It could mean it has passed through the most active LBV phase and is now evolving toward its final fate. Or it could mean that we simply have not watched long enough. The second approach has been detailed spectroscopy, the careful spreading of the star's light into its component wavelengths, in order to identify chemical elements present in the atmosphere, measure temperatures and densities at the stellar surface, and track the motion and structure of the stellar wind as it flows outward into the surrounding space. Spectroscopic observations have been made with some of the most powerful and sensitive instruments in the world, including the Space Telescope Imaging Spectrograph aboard the Hubble Space Telescope, the ultraviolet and visual Echelle spectrograph on the European Southern Observatory's Very Large Telescope in the Atacama Desert of Chile, and various other high-resolution spectrographs at observatories worldwide. These observations have confirmed the nitrogen enrichment of the star's atmosphere. They have measured the stellar wind velocity at approximately 200 kilometers per second, consistent with other blue supergiants in this mass and luminosity range. They have inferred a mass loss rate through the steady wind of roughly 100,000th of a solar mass per year, and they have established the surface temperature at approximately 12,000 to 15,000 Kelvin, the surface gravity, and other parameters that are essential inputs to the stellar evolution models. One of the most significant spectroscopic findings has been the detection of variability in certain spectral lines, particularly the hydrogen alpha line, one of the strongest emission features in the spectrum of a hot luminous star. Hydrogen alpha is produced in the star's extended wind and chromosphere, and changes in its profile, its shape, intensity, and velocity structure can reveal changes in the mass loss rate and wind geometry on timescales of weeks to months. Monitoring campaigns have shown that the hydrogen alpha profile of HD 168,625 exhibits subtle but real variations, including changes in the emission equivalent width and in the velocity of the absorption trough. These variations suggest that the stellar wind is not perfectly steady but fluctuates, perhaps driven by photospheric pulsations or by instabilities in the wind-launching region near the stellar surface. The significance of these fluctuations lies in what they might reveal about the star's deeper instabilities. In some theoretical models, the surface variability of massive supergiants is driven by subsurface convection zones associated with the iron opacity bump, the zone in the stellar envelope where partially ionized iron increases the opacity dramatically and drives convective motions. These convection zones lie only a few percent of the stellar radius below the photosphere, and their turbulent motions can generate surface velocity fields, temperature fluctuations, and brightness variations that are detectable with high-resolution spectroscopy. If the observed hydrogen alpha variability is indeed connected to this subsurface convective zone, it would provide indirect evidence of the opacity-driven instabilities that are thought to be responsible for LBV behavior more broadly. Another spectroscopic technique that has been applied to HD 168,625 is the analysis of forbidden emission lines in the circumstellar nebula. Forbidden lines, so named because they are produced by atomic transitions that are extremely unlikely under laboratory conditions, are common in low-density astrophysical plasmas, where the atoms have enough time between collisions to undergo these improbable transitions. The relative intensities of different forbidden lines of nitrogen, oxygen, and sulfur can be used to determine the electron temperature and electron density of the nebula gas, providing a detailed physical characterization of the environment surrounding the star. These diagnostics have confirmed that the nebula gas has temperatures of roughly 8,000 to 12,000 Kelvin and electron densities of a few hundred to a few thousand particles per cubic centimeter, consistent with photoionized gas, expanding away from a hot central source. The spatial distribution of these emission lines, mapped using long-slit spectroscopy and integral field spectroscopy, has revealed the velocity structure of the nebula in remarkable detail. By measuring the Doppler shifts of the emission lines at different positions within the nebula, astronomers have reconstructed the three-dimensional kinematics of the expanding hourglass. The lobes are expanding at 40 to 60 kilometers per second, with the near side of each lobe blue-shifted and the far side red-shifted relative to the star. The equatorial region shows slower expansion velocities, consistent with the denser material that forms the pinched waist of the hourglass. These kinematic measurements, combined with the angular size of the nebula on the sky and the distance to the star, allow the calculation of a kinematic age, the time since the material was ejected from the star, assuming constant expansion velocity. The result is an ejection timescale of roughly several thousand to 10,000 years, consistent with the dynamical age estimated from other methods. But spectroscopy, for all its power, tells us only about the surface. The photosphere is opaque. Every photon that reaches our telescopes was last emitted or scattered at this outermost visible layer. Everything below it, the vast bulk of the star, the convective zones, the radiative zones, the nuclear burning shells, the core itself, is hidden behind a wall of hot, dense plasma. We can measure the surface temperature to within a few hundred Kelvin. We can determine the surface chemical composition with precision. We can track the wind speed, but we cannot directly measure the core temperature, the central density, the fraction of nuclear fuel remaining, or the stage of the burning sequence. These critical parameters exist beyond our observational reach. The third approach has focused on detailed imaging and analysis of the circumstellar nebula itself, one of the most visually striking and scientifically informative features of the entire system. This has proven to be one of the richest sources of information about the star's recent past, providing a detailed fossil record of mass loss events that may have occurred thousands of years ago. The Hubble Space Telescope observed HD 168,625 in multiple filters, including narrowband filters tuned to specific emission lines of nitrogen and hydrogen, producing images that revealed the bipolar structure with remarkable clarity. The two lobes are roughly symmetric but not identical, with subtle differences in brightness and extent that suggest the ejection process was not perfectly uniform. The equatorial region shows a denser accumulation of material, consistent with the pinched waist of the hourglass shape. Observations with a Spitzer space telescope added a crucial layer of information. Operating in the mid-infrared, Spitzer detected thermal emission from dust grains in the nebula, grains that had condensed from the cooling expelled gas as it moved away from the star. The dust distribution traced the overall geometry of the nebula, and revealed additional structure within the lobes, including evidence for multiple distinct shells or layers that might correspond to separate ejection events at different times. This suggested that the nebula was not created in a single explosive event, but built up over time through repeated episodes of enhanced mass loss. The dust itself is a subject of active investigation. The composition, size, distribution, and total mass of the dust grains provide constraints on the physical conditions in the ejected material at the time of condensation. At temperatures below roughly 1,500 Kelvin, atoms and molecules in the cooling gas begin to form solid particles. Starting with the most refractory species, those with the highest condensation temperatures, such as aluminum oxide and calcium titanium oxide. As the material continues to cool, silicate minerals and iron-bearing grains condense, followed at still lower temperatures by carbonaceous compounds and ices. The infrared spectral energy distribution of the nebula, measured by Spitzer across a range of wavelengths from 3.6 to 70 microns, encodes information about the temperature, composition and size distribution of these grains. Analysis of this spectral energy distribution has revealed that the dust in the hourglass is warm, with temperatures ranging from roughly 100 to several hundred Kelvin, heated by the ultraviolet and optical radiation from the central star. The total dust mass is estimated at a few hundredths of a solar mass, which, assuming a typical gas-to-dust ratio of roughly 100, implies a total nebular mass consistent with the 1 to 2 solar masses derived from the gas emission observations. The numbers are striking when you quantify the energy involved. The total mass of the nebula, 1 to 2 solar masses, represents an enormous quantity of material, far more than the steady stellar wind alone could have supplied in the estimated age of the nebula. This implies that one or more major ejection events occurred, events that were far more violent than the star's normal wind. The kinetic energy of the expanding nebula, roughly 10 to the 47 ergs, is comparable to the energy of a small supernova. Whatever drove the ejection was extraordinarily powerful. The leading candidates are radiation-driven instabilities near the Eddington limit, the threshold at which radiation pressure equals gravitational force, or deep-seated convective instabilities that generated bursts of energy propagating outward through the star. But the imaging approach has its own limitations. The nebula tells us about the past, not the present. The material we see in the hourglass left the star thousands of years ago. The star's internal state may have changed dramatically since then. Furthermore, interpreting the three-dimensional structure of the nebula from our single viewpoint requires assumptions about the geometry, the illumination, and the density distribution. Different assumptions yield different models. The viewing angle, for example, is uncertain. We see the hourglass in projection on the sky, and the precise tilt of the bipolar axis relative to our line of sight affects how we interpret the relative sizes and brightnesses of the two lobes. Multiple research groups have proposed different viewing angles, each yielding slightly different inferences about the true structure and mass of the nebula. The fourth approach has involved theoretical stellar evolution modeling, the construction of detailed computer simulations that track the life of a massive star from birth to death. These models solve the equations of stellar structure, a set of four-coupled differential equations that describe how pressure, temperature, luminosity, and mass are distributed from the center of the star to its surface. Added to these are equations describing nuclear reaction networks, tracking dozens or hundreds of isotopes as they are created, destroyed, and transformed by fusion reactions. Models also incorporate prescriptions for energy transport, describing how energy moves outward through the star by radiation in some regions and by convection in others, and prescriptions for mass loss, describing how the stellar wind strips material from the surface. Modern stellar evolution codes like MESA, the Modules for Experiments in Stellar Astrophysics, developed by Bill Paxton and collaborators beginning in 2011, can track the evolution of a massive star from the zero-age main sequence through all the post-main sequence phases to the onset of core collapse. These codes represent a tremendous achievement of computational astrophysics. They can reproduce the general evolutionary tracks of massive stars, predict the timescales for each burning phase, calculate the chemical yields of the supernova, and determine whether the star ends its life as a red supergiant, a blue supergiant, or a Wolf-Rayet star. But the models fail, or at least struggle, in several important areas. The treatment of mass loss is one of the most significant weaknesses. Standard models use empirical prescriptions, formulas derived from observations that relate the mass loss rate to the star's luminosity, temperature, and metallicity. These prescriptions are averages, derived from samples of stars, and they may not accurately capture the behavior of individual objects, especially during extreme events like LBV eruptions. The giant eruptions that produce nebulae, like the one around HD 168,625, are not included in standard prescriptions because they are too rare, too brief, and too poorly understood to be parameterized. They are treated as external events, bolted onto the models after the fact, rather than emerging naturally from the physics. The treatment of convection is an even deeper problem. Convection, the turbulent mixing of material by buoyant fluid motions, is a fundamentally three-dimensional chaotic process, but standard stellar evolution models are one-dimensional. They describe the star as a series of concentric spherical shells and use approximate theories to represent the effects of convection. The most common approximation is mixing length theory, developed by Ludwig Biermann in the 1930s and formalized by Erika Bohm-Vitens in the 1950s. This theory parameterizes convective energy transport using a single adjustable parameter, the mixing length, typically calibrated against observations of the Sun. Mixing length theory has been remarkably successful for many applications, but it is known to be inaccurate in several important regimes, particularly near the boundaries of convective zones, where overshooting of convective plumes can mix material beyond the region predicted by the standard theory, and during the late evolutionary stages, when the timescale for convective turnover becomes comparable to the timescale for nuclear burning. Three-dimensional hydrodynamic simulations of convection in massive stellar interiors, run on some of the most powerful supercomputers in the world, have revealed phenomena that one-dimensional models cannot capture. Convective plumes generated by burning in the oxygen and silicon shells can reach velocities of hundreds of kilometers per second. They generate internal gravity waves that propagate through the star, transporting energy and angular momentum across vast distances. They can trigger episodes of violent mixing, dredging up fresh fuel into burning regions and injecting processed material into the outer layers. These simulations suggest that the final years and decades of a massive star's life may be far more dynamic and turbulent than the smooth evolutionary tracks predicted by one-dimensional models would indicate. The implications for HD 168,625 are significant. If the star's interior is indeed experiencing the kind of convective turbulence revealed by three-dimensional simulations, then its outer layers may be influenced by deep-seated instabilities that we cannot detect from the surface. There may be episodes of enhanced mass loss, shell ejections, and variability driven by processes occurring thousands of kilometers below the photosphere. The apparently quiescent surface may conceal an interior in violent upheaval. A fifth angle of investigation involves the detailed comparison of HD 168,625 to the full population of known supernova progenitors and LBVs. This comparative approach grounds theoretical predictions in observational reality. By studying the properties of stars that have already exploded and comparing those properties to stars that have not yet exploded but share similar characteristics, astronomers can identify the most likely evolutionary pathways and predict the outcomes. The comparison to Eta Carinae has already been discussed. Despite the shared Hourglass nebula morphology, the two stars differ substantially. Eta Carinae is far more luminous, roughly 5 million solar luminosities compared to 300,000 for HD 168,625. Eta Carinae is also much more massive, with a combined system mass estimated at over 100 solar masses. And Eta Carinae has been observed to undergo dramatic eruptions within recorded history while HD 168,625 has been comparatively quiet during the era of modern observations. These differences suggest that the two stars, while belonging to the same general class, may be at different evolutionary stages, or may follow different evolutionary paths to different endpoints. The comparison to the SN 1987A progenitor remains the most compelling. The match in luminosity, temperature, spectral type, nebular morphology, and chemical composition is detailed and specific. The key difference is existential. Sanderleak -69 degrees, 202 exploded. HD 168,625 has not, yet. But if the similarity in observable properties reflects a similarity in internal state, then the implication is stark. This star may be in the same final evolutionary phase that Sanderleak -69 degrees 202 was in when it produced SN 1987A. A sixth angle involves the search for binary companions. As mentioned, no companion has been definitively confirmed. High-resolution spectroscopic monitoring has been used to look for the periodic radial velocity variations that would betray a companion's gravitational tug. These observations have been complicated by the star's strong and variable stellar wind, which can introduce spectral line profile variations that mimic or mask orbital signatures. Speckle interferometry and adaptive optics imaging have been used to search for visual companions at close separations without definitive success. The question of whether HD 168,625 has a companion remains one of the important unknowns in the system. If a companion does exist, it could profoundly alter the star's evolutionary trajectory. Binary interactions, including mass transfer, common envelope evolution, and tidal effects, can strip mass from the primary star more efficiently than single-star winds alone. They can modify the star's rotation rate and internal mixing. They can alter the final mass at core collapse and therefore the type of supernova produced. The possibility of a hidden companion is not merely an academic curiosity. It could be the key to understanding the star's past and predicting its future. A seventh approach, still in its infancy for massive supergiants, is astroseismology, the study of stellar oscillations to probe the interior structure of stars. Just as seismologists on Earth use earthquake waves to map the planet's internal layers, astrophysicists can use the natural pulsations of stars to infer properties of their interiors that are otherwise invisible. For solar-type stars and red giants, astroseismology has been spectacularly successful, thanks to the precise, continuous photometric measurements provided by space missions like the Kepler telescope and its successor TESS, the Transiting Exoplanets Survey satellite. Thousands of stars have had their internal rotation rates, core densities, and evolutionary states determined through careful analysis of their oscillation frequencies. For massive blue supergiants, however, the picture is far less clear. These stars do pulsate, driven by mechanisms related to the opacity of iron and iron group elements in their envelopes, the same opacity effects that drive the LBV instability. But the pulsations are irregular, with long periods measured in days to weeks, and small amplitudes that can be difficult to distinguish from the stochastic variability caused by convective motions in the stellar atmosphere. Extracting clean oscillation frequencies from this noisy signal is a formidable challenge. Nevertheless, recent theoretical work has shown that certain combinations of pulsation modes, if detected, could provide direct constraints on the core mass, the extent of the convective core, and even the burning stage of the stellar interior. A detection of gravity modes, oscillations driven by buoyancy, in the radiative layers of the star, would be particularly valuable, as these modes penetrate deep into the stellar interior and carry information about conditions near the core. Gravity modes have been detected in other massive stars, notably in the blue supergiant HD 46328, where they revealed a rapidly rotating core, challenging existing models of angular momentum transport. Whether similar detections are possible for HD 168,625 depends on the amplitude of the oscillations and the precision of the photometric monitoring, but the theoretical framework is in place, waiting for the data. An eighth line of investigation involves spectropolarimetry, the measurement of the polarization of the star's light as a function of wavelength. When light passes through or is scattered by an asymmetric distribution of matter, it becomes partially polarized, with the electric field of the light waves preferentially oscillating in one direction. By measuring this polarization across the star's spectrum, astronomers can infer the geometry of the circumstellar environment on scales too small to resolve directly. Spectropolarimetric observations of HD 168,625 have revealed a variable polarization signature that indicates the stellar wind is not perfectly, spherically symmetric. There is a preferred axis, consistent with the orientation of the bipolar nebula, suggesting that the same asymmetry responsible for shaping the hourglass is present in the current-day wind on much smaller scales. This is significant because it constrains models of the mass loss geometry and provides evidence that the physical mechanism driving the bipolar outflow, whether it is rotation, magnetic fields, or some combination of both, is still operating today. The question of magnetic fields deserves particular attention. Some models of LBV eruptions and bipolar outflows invoke magnetic fields as the mechanism for channeling the mass loss into the preferred directions. A strong ordered magnetic field, with a dipole axis aligned with the rotation axis, would naturally concentrate the stellar wind toward the equator, creating the density enhancement that diverts subsequent wind material toward the poles. Magnetic fields could also play a role in triggering and shaping the eruptions themselves through magnetically driven instabilities in the stellar atmosphere. However, detecting magnetic fields in massive supergiants is extremely difficult. The spectral lines are broadened by the high temperatures and the fast stellar wind, making the subtle Zeeman splitting that reveals the presence of a magnetic field nearly impossible to resolve. Upper limits on the surface magnetic field of HD 168,625 have been estimated from high-resolution spectropolarimetry at roughly a few hundred Gauss, but these limits are not stringent enough to rule out the presence of a dynamically significant field. The role of magnetism in the star's evolution and mass loss remains an open question. Future observations promise to push the boundaries of what we can learn. The James Webb Space Telescope, launched in December 2021, operates at mid-infrared wavelengths with sensitivity and angular resolution far surpassing any previous infrared observatory. JWST's instruments can probe the detailed structure and composition of the Hourglass Nebula at wavelengths where warm dust emits most strongly, revealing structures too faint or too deeply embedded for earlier telescopes. Observations with JWST's mid-infrared instrument and near-infrared camera could map the dust distribution within the hourglass at unprecedented resolution, identify layers or substructures corresponding to individual ejection episodes, and measure the chemical composition of the dust grains themselves, distinguishing between silicate and carbonaceous grains, and thereby constraining the chemistry of the gas from which they condensed. These observations would provide a much more detailed reconstruction of the star's mass loss history than is currently possible. Ground-based facilities are also advancing. The extremely large telescope currently under construction by the European Southern Observatory in the Atacama Desert of Chile will have a primary mirror 39 meters in diameter, dwarfing existing 8 to 10 meter class telescopes. When it begins observations, planned for later in this decade, the ELT will provide angular resolution sufficient to resolve structures in the immediate vicinity of the star within the innermost regions of the nebula, where the current wind interacts with previously ejected material. Combined with high-resolution spectrographs and adaptive optics systems that correct for atmospheric turbulence in real time, the ELT could measure the velocity structure of the wind on scales of a few hundred astronomical units, probing the transition region where the fast blue supergiant wind collides with the slower material from earlier evolutionary phases. The challenge of modeling is also evolving. Beyond the one-dimensional mesomodels, a new generation of multidimensional simulations is beginning to bridge the gap between stellar evolution and stellar hydrodynamics. Groups at institutions including the Max Planck Institute for Astrophysics, the University of Arizona, and Caltech are running three-dimensional simulations of the final years of massive stars' lives, tracking the convective turbulence in the oxygen and silicon-burning shells with enough spatial resolution to capture the development of individual convective plumes and the waves they generate. These simulations are computationally expensive, requiring millions of processor hours on the world's largest supercomputers, and they can cover only the final minutes, hours, or days of the star's life before collapse. But they have already revealed surprises. One finding is that the convective shells can become violently asymmetric in the final minutes before collapse, with large-scale plumes reaching upward into overlying layers and generating substantial perturbations in the density and velocity structure of the star. These perturbations can seed asymmetries in the supernova explosion itself, influencing the direction of the shock wave, the distribution of the ejector, and even the kick velocity imparted to the resulting neutron star. Another finding is that gravity waves generated by the convective shells can transport significant amounts of energy to the stellar surface, potentially causing observable surface variability in the final weeks or months. If these predictions are correct, then careful monitoring of massive supergiants like HD 168,625 might eventually reveal the subtle signs of approaching collapse, the tremors before the earthquake. But we are not there yet. The models are still too coarse, the observations too sparse, and the theoretical framework too uncertain to make reliable predictions about any individual star. We can say that HD 168,625 will explode. We can say with confidence that the explosion, when it comes, will be extraordinary, one of the most energetic events in the modern history of our galaxy. But we cannot say when. Not within a factor of 1,000. Not within a factor of 10,000. And that uncertainty, that yawning gap between what we know and what we need to know, is the defining characteristic of this entire scientific problem. The math is striking when you consider the observational challenge from another perspective. The star emits roughly 10 to the 39 watts of power at a distance of 7,200 light-years, or roughly 6.8 times 10 to the 19 meters. Only a tiny fraction of that light reaches Earth. A single telescope mirror, even the largest, intercepts an almost infinitesimally small fraction of the star's total output. We are trying to diagnose the internal state of an object millions of kilometers across, burning at hundreds of millions of degrees, from a distance of 68 quintillion meters, using the handful of photons that happen to land on our mirrors. It is like trying to determine the temperature and composition of a campfire by standing in another country and catching a single spark on a piece of glass, and yet we have learned an enormous amount. That is the remarkable thing. From those scattered photons, we have reconstructed the star's luminosity, its temperature, its chemical composition, its wind speed, its mass loss rate, its distance, the structure and mass and kinematics of its nebula, and its likely evolutionary state. We have compared it to other stars that have already died and drawn conclusions about its future. We have built theoretical models that predict in broad strokes what will happen when the star's core finally runs out of fuel. The depth of what we have accomplished, given the almost absurd limitations of our vantage point, is one of the great achievements of modern astrophysics, but the fundamental limitation remains. We cannot see the core. We cannot measure when the end will come. If HD 168,625 were to explode at this very instant, we would not know for approximately 7,200 years. The light from the explosion would begin its journey today and arrive around the year 9,200. Conversely, if we observe the supernova tonight, the actual event occurred around 5,174 years before the Common Era. We are always looking at the past. The star we see tonight may already be dead, its core already collapsed, its outer layers already expanding into space, the light of its death racing toward us across the galaxy, say. We would not know. We cannot know. Not until the photons arrive. There is one technology, however, that could provide earlier warning: neutrino detectors. When a massive star's core collapses, roughly 99% of the gravitational energy released is carried away not by photons but by neutrinos, subatomic particles of nearly zero mass that interact only through the weak nuclear force and gravity. These neutrinos stream outward from the collapsing core at nearly the speed of light, passing through the star's outer layers as though they were transparent. They escape the star hours before the shockwave reaches the surface and the first photons of the supernova are released. This means that neutrino detectors on Earth would register a burst of neutrinos several hours before the supernova becomes visible in the sky. This is exactly what happened with SN 1987A. On February 23, 1987, 3 neutrino detectors around the world registered a burst of approximately 24 neutrinos over about 13 seconds. The Kamiokande 2 detector in Japan recorded 12 events. The IMB detector in Ohio recorded 8. The Baksan detector in the Soviet Union recorded 5. From those 25 or so particles, extracted from a total emission of roughly 10 to the 58 neutrinos, physicists confirmed the basic theoretical picture of core collapse supernovae that had been developed over the preceding decades. The detection earned Masatoshi Koshiba a share of the Nobel Prize. Today, neutrino detectors are far more capable. Super Kamiokande in Japan, containing 50,000 metric tons of ultra-pure water and 11,200 photomultiplier tubes, could detect thousands of neutrinos from a galactic supernova. The IceCube Neutrino Observatory at the South Pole, using a cubic kilometre of Antarctic ice as its detector medium, could detect tens of thousands. Future detectors like Hyper Kamiokande and DUNE, the Deep Underground Neutrino Experiment, will push the sensitivity even higher. The Supernova Early Warning System, known as NUS, is a global network of neutrino detectors designed to provide automated alerts when a coincident burst of neutrinos is detected, giving astronomers minutes to hours of advance warning before the light of the supernova arrives. If HD 168,625 explodes, and when it does, we will be as prepared as our technology allows. The neutrinos will come first, a silent herald racing ahead of the light. Then the sky will change. A new star will appear in Sagittarius, brightening over hours to its peak, dominating the night sky for weeks. And the Hourglass Nebula, that delicate structure of nitrogen and dust that served as our warning sign, will be swept up in the expanding debris, torn apart by the blast wave, incorporated into the much larger and more violent structure of the supernova remnant. The hourglass was always a message. We are learning, slowly, painstakingly, to read it. But some parts of the message may only become clear after the star is gone. There is a deeper truth lurking beneath the science of HD 168,625, a truth that transcends the equations and the spectral analyses and the computer models. It is a truth about the nature of stellar death itself, and about the relationship between destruction and creation in a universe governed by the blind, relentless, and breathtakingly elegant laws of physics. We speak of supernovae as explosions, as catastrophes, as the violent ends of stars, and they are all of those things. A core collapse supernova releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. The shockwave that tears through the Dyson star heats matter to billions of degrees. The debris expands at tens of thousands of kilometers per second, carrying enough kinetic energy to reshape entire regions of interstellar space. Within a certain radius, a supernova sterilizes everything. Planets are stripped of their atmospheres. Moons are vaporized. Any life that might exist within a few dozen light years would face a radiation bath capable of destroying the ozone layers of terrestrial worlds and flooding their surfaces with lethal ultraviolet light. But a supernova is also something else entirely. Something that is easy to overlook when the scale of the destruction dominates the narrative. A supernova is a factory. It is the mechanism by which the universe creates complexity. It is the furnace in which the heaviest elements are forged and the distribution system by which they are scattered into the cosmos. Without supernovae, the periodic table would end at helium, and the universe would be a vast, cold, featureless expanse of hydrogen and helium gas, forever incapable of producing anything as complex as a molecule, a mineral, a planet, or a living cell. Every heavy element in the periodic table, every atom of carbon, nitrogen, oxygen, silicon, iron, gold, platinum, and uranium, was either forged in the interior of a star during its lifetime or created in the cataclysmic instant of a supernova explosion, or in the aftermath of events like the collision of neutron stars. The hydrogen and helium that make up the bulk of the cosmos were produced in the first few minutes after the Big Bang, roughly 13.8 billion years ago, during the epoch of primordial nucleosynthesis, when the entire universe was a hot, dense plasma. But everything else, everything heavier than helium on the periodic table, was manufactured by stars. The processes by which these elements are created are numerous and varied, and they depend critically on the environment. Elements up to iron are produced primarily by nuclear fusion in stellar cores, through the sequence of burning stages that has already been described. But elements heavier than iron, from cobalt and nickel through the rare earth metals, through gold and platinum and lead, all the way up to uranium, cannot be produced by fusion alone, because fusing nuclei heavier than iron costs more energy than it releases. Instead, these heaviest elements are built by a different mechanism, the capture of free neutrons by existing atomic nuclei. When a nucleus captures a neutron, it becomes a heavier isotope. If the resulting isotope is unstable, it undergoes beta decay, converting a neutron into a proton, and thereby moving one step up the periodic table to the next element. Through successive rounds of neutron capture and beta decay, elements of progressively higher atomic number can be constructed, one step at a time, building up the heaviest atoms in the universe. There are two principal pathways for this process, distinguished by the rate at which neutrons are captured relative to the rate of beta decay. The slow neutron capture process, called the S process, occurs in the interiors of evolved low-mass and intermediate-mass stars, particularly during the asymptotic giant branch phase, when thermal pulses in the helium-burning shell generate a modest flux of free neutrons. In the S process, neutron captures occur slowly enough that unstable isotopes have time to undergo beta decay before capturing another neutron. This traces a path through the chart of nuclides that follows the valley of beta stability, producing elements like strontium, barium, and lead in predictable abundance ratios that match observations of S-process enriched stars and presolar grains extracted from meteorites. The rapid neutron capture process, called the R process, requires an environment with an extraordinarily high density of free neutrons, so intense that nuclei capture many neutrons in rapid succession, far faster than they can decay. This extreme neutron bath drives nuclei far from the valley of stability, into highly neutron-rich territory, where they undergo cascades of beta decay after the neutron flux subsides, producing a distinct pattern of elements. The R process is responsible for approximately half of all the elements heavier than iron, including many of the most valued and familiar: gold, platinum, iridium, thorium, and uranium. The astrophysical site of the R process was debated for decades. Core collapse supernovae were long considered the primary candidate, as the intense neutrino wind emerging from the newborn neutron star generates conditions that might support rapid neutron capture. But models struggled to reproduce the observed abundance pattern. The situation changed dramatically in August 2017, when the LIGO and Virgo gravitational wave detectors observed the merger of two neutron stars, an event designated GW170817, and the accompanying electromagnetic counterpart, a kilonova, was found to show the unmistakable spectral signatures of R process elements. The tidal disruption of the neutron stars ejected highly neutron-rich material into space, and the rapid neutron capture in this material produced heavy elements in quantities consistent with the observed abundances. Neutron star mergers are now considered a major, perhaps dominant, source of R process elements in the universe. Both the S process and the R process are consequences of stellar evolution. The S process occurs in lower mass evolved stars. The R process occurs in the aftermaths of massive star deaths, whether through the supernovae that create neutron stars or through the subsequent mergers of neutron star pairs formed in binary systems. In either case, the heavy elements are created and then dispersed into the interstellar medium, where they become available for incorporation into the next generation of stars and planets. HD 168,625, when it eventually explodes, will contribute to this cosmic inventory. Its supernova may produce R-process elements in the neutron-driven wind from the proto-neutron star. The neutron star or black hole remnant it leaves behind me, if it has a companion, eventually merge with that companion billions of years later, producing yet another burst of R-process nucleosynthesis. The cycle of element creation and dispersal extends across multiple events, multiple timescales, and multiple mechanisms, each building on the products of the last. The carbon in your body was fused from helium nuclei in the core of a star that lived and died billions of years before the sun was born. 3 helium nuclei, each with 2 protons and 2 neutrons, came together in a process called the triple alpha reaction, producing a single carbon nucleus with 6 protons and 6 neutrons. This reaction occurs at temperatures above 100 million Kelvin, deep in the cores of massive stars and in the shells of aging red giants. The carbon in your DNA, in the proteins that build your muscles, in the sugars that fuel your brain, every atom of it was born in a stellar furnace and released into space by the death of its parent star. The iron in your blood was produced in the final seconds of a massive star's life. During the silicon burning phase that lasts only 1 day, silicon nuclei, bombarded by intense radiation and colliding with each other at enormous energies, fuse into iron and nickel isotopes, building up the iron core that will ultimately trigger the star's collapse. The iron atoms that carry oxygen through your bloodstream today, the iron atoms in the hemoglobin molecules that keep you alive at this very moment, were forged in the core of a dying star and scattered into space by the supernova that followed. They drifted through the interstellar medium for millions or billions of years before being swept up into the collapsing cloud of gas that formed our sun and solar system 4.6 billion years ago. Let that sink in. You are not merely made of atoms. You are made of atoms that have been inside stars. The calcium in your bones was produced by oxygen burning in a massive stellar core. The phosphorus in your DNA was forged in the silicon-burning shell of a supergiant. The oxygen you are breathing right now was created by helium fusion in a star that no longer exists. You are, in a literal and chemically verifiable sense, made of dead stars. This is not a metaphor. It is not poetic license. It is a measured, quantified, spectroscopically confirmed fact of nuclear physics and stellar astrophysics. HD 168,625 is in the process of creating the next generation of these elements right now, at this very moment, as you listen to these words. In its core, nuclear reactions are fusing lighter elements into heavier ones, building up the inventory of carbon, nitrogen, oxygen, silicon, and iron that will be released into the galaxy when the star explodes. The nitrogen in the Hourglass nebula is a down payment, material that has already been processed and expelled. The main delivery, the bulk of the heavy elements, is still locked inside the star, waiting for the final catastrophe to set them free. This is the great cycle of stellar evolution, and it is one of the most fundamental processes in the universe. Stars form from clouds of gas and dust in the interstellar medium. These clouds, called molecular clouds or giant molecular clouds, are vast, cold, dark structures, sometimes spanning hundreds of light years, containing enough material to form thousands or millions of stars. When a region within such a cloud becomes dense enough, it collapses under its own gravity. The collapsing material heats up, spins faster as it contracts, and eventually ignites nuclear fusion at its core. A star is born. The conditions required for this collapse are specific and not always met. A molecular cloud must reach a critical density, sometimes called the Jeans mass after the British physicist Sir James Jeans, who first derived the criterion in the early 20th century, before gravitational attraction can overcome the thermal pressure and turbulent motions that resist collapse. In practice, collapse is often triggered by external events: a passing spiral arm that compresses the gas, the expanding bubble of a nearby stellar wind, the collision of two clouds, or, as discussed, the shockwave from a nearby supernova. Once collapse begins, the process is self-reinforcing. The denser the core becomes, the stronger its gravitational pull, and the faster it accretes material from its surroundings. Within a few 100,000 years, the central temperature reaches roughly 10 million Kelvin, deuterium, and then hydrogen fusion ignites. and a protostar becomes a true star. The star burns for millions or billions of years, depending on its mass, fusing hydrogen into helium, and, if massive enough, continuing through the sequence of heavier elements. Throughout its life, it loses mass through stellar winds, enriching the surrounding space with processed material. When it dies, whether as a planetary nebula from a low-mass star or as a supernova from a massive one, it returns much of its material to the interstellar medium, enriched with the heavy elements it forged in its interior. This enriched material mixes with the existing gas and dust, and eventually, some of it is swept up into a new collapsing cloud, where it forms a new generation of stars and potentially planets. The process is cyclical, self-sustaining, and ongoing. It has been operating continuously for over 13 billion years, and it will continue for billions more, as long as raw material remains available and the conditions for star formation persist. Each generation of stars is chemically richer than the last. The first stars, formed from the pristine hydrogen and helium of the early universe, contained no heavy elements at all. They are called population 3 stars, and none have been directly observed because they all died billions of years ago. Their lives measured in millions of years. Their supernovae enriched the surrounding gas with the first heavy elements, carbon, oxygen, iron, and others. The next generation of stars formed from this slightly enriched material. They were population 2 stars, still metal poor by modern standards but richer than the first generation. Their deaths added more heavy elements to the cosmic inventory. Eventually, after multiple stellar generations, the interstellar medium became enriched enough to form population 1 stars like our Sun, metal-rich objects that contain roughly 2% of their mass in elements heavier than helium. 2% may sound small, but it makes all the difference. That 2% includes the silicon and iron that form the core of the Earth. It includes the carbon, nitrogen, oxygen, and phosphorus that are the building blocks of life. It includes the water that fills the oceans and the oxygen that fills the atmosphere. Without those heavy elements seeded into the cosmos by billions of years of stellar death, planets like Earth could not exist. Life as we know it could not arise. The evidence for this story is written in the oldest rocks of our solar system, meteorites, the fragments of asteroids that formed in the earliest days of the solar system 4.6 billion years ago, contain tiny grains of material that predate the Sun itself. These presolar grains, identified by their anomalous isotopic ratios, were forged in the outflows and explosions of stars that lived and died before our solar system formed. Some carry the isotopic signatures of the S process, marking them as products of evolved low-mass stars. Others carry R process signatures, linking them to supernovae or neutron star mergers. A few contain the decay products of short-lived radioactive isotopes like aluminum-26 and iron-60. Isotopes with half-lives of only hundreds of thousands to millions of years, meaning they must have been produced shortly before the solar system formed, almost certainly by a supernova that occurred in the vicinity of the collapsing molecular cloud from which the Sun was born. This nearby supernova may have done more than just contribute material. Some models suggest that the shock wave from a nearby supernova may have triggered the gravitational collapse of the presolar cloud itself, compressing a region of gas and dust that was on the edge of stability and initiating the process that led to the formation of the Sun and its planets. If this is correct, then our solar system owes its very existence to the death of a massive star, a star that, millions of years before the Sun ignited, went through the same sequence of nuclear burning stages, the same exhaustion of fuel, the same catastrophic core collapse, and the same violent dispersal of enriched material that awaits HD 168,625. We are not merely made of stellar debris. We may exist because a star died in precisely the right place at precisely the right time. This is not science fiction. This is the established, observationally confirmed, and theoretically understood story of chemical evolution in the universe. Every element on Earth that is heavier than hydrogen and helium was manufactured in the interior of a star or in the explosion that ended its life. Our Sun is a third-generation star, formed from material that had been processed through at least 2 previous stellar generations. We are the beneficiaries of a chain of stellar deaths that stretches back billions of years to the very first stars that formed in the infant universe. And HD 168,625 is a link in that chain. Its death, when it comes, will be violent and spectacular beyond anything in human experience. But it will also be generative, profoundly and necessarily creative. The supernova will inject heavy elements into the interstellar medium, enriching the raw material from which future stars and planets will form. Billions of years from now, the atoms that are currently locked inside this star may be part of a rocky planet orbiting a star that does not yet exist, in a solar system that will not form for eons. Those atoms may be part of an ocean, part of an atmosphere, part of a molecule, part of a cell, part of something alive. Let that sink in. The atoms in this dying star may one day be the atoms in a living thing. The nitrogen in the Hourglass nebula, the same nitrogen that was processed through the CNO cycle in the star's core and expelled during a violent eruption thousands of years ago, may eventually be incorporated into the atmosphere of a distant future world. It may become part of the nitrogen gas that fills the sky of that world, or part of the amino acids that build the proteins of whatever organisms evolve there. The connection between a dying star and the possibility of future life is not speculative or sentimental. It is chemical, it is physical, it is quantifiable. It is the way the universe actually works. There is something else about the hourglass shape that deserves contemplation. An hourglass is a timekeeper. It is one of humanity's oldest instruments for measuring the passage of time, used for centuries before the development of mechanical clocks. Sand flows from one chamber to another through a narrow neck, and when the upper chamber empties, the allotted time has passed. The fact that HD 168,625 has sculpted its dying breath into this shape is, of course, a coincidence, a product of physics, not intention. The universe does not deal in symbolism. Rotation rates and mass-loss geometries and wind interactions do not know or care what shapes mean to human beings. But we deal in symbolism. We are meaning-making creatures, and we cannot help but see, in that glowing hourglass of nitrogen and dust, a reminder that all things are temporary. Stars are temporary. They burn for millions or billions of years, but they burn out. Planets are temporary. The Earth will eventually be consumed by the Sun as it expands into a red giant, roughly 5 billion years from now. Species are temporary. 99% of all species that have ever lived on Earth are now extinct. Civilizations are temporary. Every empire in human history has risen and fallen. The universe itself, as far as our best models can determine, is evolving toward a state of maximum entropy, a condition of perfect disorder and uniform temperature in which no useful energy remains and no structure can survive. This state, sometimes called the heat death of the universe, lies unimaginably far in the future, trillions upon trillions of years from now. But the trajectory is set. The stars will eventually stop forming. The last stellar embers will fade. The galaxies will disperse. The black holes will evaporate through Hawking radiation. And everything that ever existed, every star, every planet, every creature that ever drew breath or formed a thought, will be reduced to a thin, cold scattering of particles and radiation, slowly cooling toward absolute zero. We live in a window. A brief, improbable, cosmically thin window of time during which conditions permit the existence of complex structures, stars burning, planets forming, oceans of liquid water, organic molecules assembling into self-replicating systems, consciousness emerging from the electrochemistry of evolved nervous systems. This window will not last forever. It is already closing, in the sense that the raw materials for new stars are slowly being used up, and the universe is expanding and cooling. But right now, right here in this particular cosmic moment, the conditions exist for matter to know itself, for atoms forged in stellar cores to assemble into structures that can look back at the stars that made them and understand the process. Something is wrong with our assumptions if we think of death as the opposite of creation. In the cosmos, death is a form of creation. The death of a star is the birth of heavy elements. The death of one stellar generation is the necessary precondition for the birth of the next. Without supernovae, the universe would contain nothing but hydrogen and helium. Without the deaths of massive stars like HD 168,625, There would be no carbon, no oxygen, no iron, no silicon, no planets, no oceans, no atmospheres, no life. We owe our existence to the deaths of stars. Every atom in our bodies is a memorial to a star that no longer shines. The hourglass is running, the sand is flowing, and we are watching from across the galaxy, tiny and brief and infinitely curious, trying to understand the mechanism, trying to read the cosmic clock, trying to predict when the last grain will fall. What does HD 168,625 mean for us? Not for astronomy as a discipline, not for the equations and models and peer-reviewed papers that fill the academic journals, but for us as human beings. For a species that has existed for perhaps 300,000 years on a small rocky planet orbiting an unremarkable star in the suburbs of an unremarkable galaxy, looking up at a sky full of light that it has only recently, in the last few centuries of its long existence, begun to understand. The implications unfold in layers, and the first layer is the simplest and perhaps the most jarring to contemplate directly. The universe is not safe. We live in a cosmos of extraordinary violence, governed by forces that are as powerful as they are indifferent. The nuclear reactions that sustain stars are the same reactions that power hydrogen bombs. The gravitational force that holds planets in their orbits is the same force that crushes stellar cores into neutron stars and black holes. The radiation that warms our skin on a summer afternoon is the same radiation that, in sufficient intensity, can sterilize entire worlds. The laws of physics do not negotiate. They do not make exceptions. They operate with perfect consistency, and their consequences include both the gentle warmth of sunlight and the annihilating violence of a supernova. HD 168,625 at 7,200 light-years is far enough from Earth that its eventual supernova poses no direct threat to our planet. The radiation and debris from the explosion will be diffused across such an enormous volume of space by the time they reach our solar system that their effects will be negligible. We will observe the event. We will measure it with every instrument we possess. Scientists will study it for centuries, but we will not be harmed by it. This is an accident of geometry, a fortunate consequence of the vast distances between stars. If this star were within 30 to 50 light-years, the situation would be profoundly different. The gamma radiation from a supernova at that distance could deplete Earth's ozone layer by 50% or more, exposing the surface to intense ultraviolet radiation from the sun for years or decades. Marine ecosystems, which depend on photosynthetic organisms in the upper ocean layers, would be devastated. Terrestrial life would face a cascade of ecological disruption. So some paleontologists have suggested that past mass extinctions, including the late Ordovician extinction roughly 444 million years ago, may have been triggered or exacerbated by nearby supernovae, though the evidence remains debated. But the fact that this particular star poses no direct threat does not diminish the philosophical weight of its existence. It is a reminder that our safety is contingent. The cosmos is populated with objects and processes of immense destructive power, from nearby supernovae to asteroid impacts to gamma-ray bursts that can deliver lethal radiation from thousands of light-years away. We have survived this long partly through the fortunate placement of our solar system in a relatively quiet region of the Milky Way, away from the dense stellar clusters and active star-forming regions where supernovae are most common. Our galactic neighborhood is, by the standards of the universe, peaceful. But neighborhoods evolve. Stars are born and die. The galaxy rotates. And the conditions that have kept us safe for 4.6 billion years are not guaranteed to persist indefinitely. The cosmic lottery has favored us so far, but lotteries by their nature do not promise continued favor. The same physical processes that created the conditions for our existence are also capable, under slightly different circumstances, of destroying those conditions utterly. The universe is not hostile. It is indifferent, and indifference in a cosmos of this scale and power can be more dangerous than malice. The second layer of implication is scientific. HD 168,625 is a test case. It is a laboratory for studying the physics of massive stellar evolution, mass loss, and pre-supernova instability. It is a benchmark against which theoretical models will be measured, a data point that constrains our understanding of how stars in this mass range behave as they approach the end of their nuclear fuel supply. If and when this star explodes, it will be the first core collapse supernova in the Milky Way observed with modern instruments. The last galactic supernova observed by astronomers were Kepler's supernova in 1604, more than 420 years ago now. That event occurred before the invention of the telescope as a scientific instrument, and the observations made by Johannes Kepler and his contemporaries, while invaluable for the historical record, were limited to naked eye estimates of brightness, colour, and position in the sky. Today, we are incomparably better prepared. Neutrino detectors spanning the globe, including Super Kamiokande, IceCube, and the Sudbury Neutrino Observatory's successor experiments, are online and waiting. Gravitational wave detectors, LIGO and Virgo and CAGRA, and their planned successors, might detect the asymmetric core collapse if it produces significant gravitational radiation. Telescopes covering the entire electromagnetic spectrum, from long-wavelength radio waves to high-energy gamma rays, are prepared to respond within minutes of an alert. The data from a galactic supernova would test our models of core collapse, neutrino transport, nucleosynthesis, and shock propagation against direct observation. It would reveal the internal structure of the progenitor star with a precision no other method can achieve. It would tell us whether the collapse produces a neutron star or a black hole, and it would provide a calibration point, a fixed anchor against which all future models of massive stellar evolution and death would be measured. The scientific value of such an event is, in a very real sense, incalculable. The coordination required for such an observation is itself a remarkable human achievement. The SNUDUS network links neutrino detectors across multiple continents, multiple time zones, and multiple national scientific programs into a single automated alert system. When two or more detectors simultaneously register a burst of neutrinos consistent with a core collapse event, the system generates an alert within minutes, distributing it to observatories worldwide through a cascade of automated notifications. Telescopes can then slew to the approximate sky region, narrowing the location by cross-referencing the neutrino arrival times at different detectors. The entire process, from the first neutrino interaction in an underground tank of water or ice to the first photon captured by a telescope pointed at the right patch of sky, might take less than an hour. Humanity has built, without any guarantee that it will be needed in our lifetimes, a planetary-scale early warning system for the death of a star. The ambition and the patience of that undertaking are themselves a testament to the same impulse that drives the study of HD 168,625. We watch because we want to understand. We prepare because understanding requires readiness. And we do both knowing that the payoff may come tomorrow or may come in 10,000 years. There is also the question of what the supernova remnant would look like, decades and centuries after the explosion. The expanding debris would interact with the Hourglass Nebula, with the surrounding interstellar medium, and eventually with the broader galactic environment. The remnant would emit across the entire electromagnetic spectrum as the shock wave heated and compressed the surrounding gas. X-ray observatories would detect the million-degree plasma behind the shock front. Radio telescopes would detect synchrotron radiation from electrons spiraling in the amplified magnetic fields of the remnant. The chemical composition of the ejecta, mapped through the spectral lines of individual elements at known expansion velocities, would provide a direct test of nucleosynthesis models. We would, for the first time in the history of astronomy, be able to compare the predicted chemical yields of a supernova model against the measured composition of the actual ejecta from a star whose properties we had characterized in detail before the explosion. The importance of this cannot be overstated. It would close the loop between prediction and observation, between theory and nature, in a field that has been forced to operate on indirect evidence for its entire existence. The third and deepest layer of implication is personal. It is about time and about our place within it. HD 168,625 has existed for millions of years. It formed from a collapsing cloud of gas and dust in the Milky Way, ignited its core fusion, joined the main sequence, evolved off it, entered the LBV phase, shed its hourglass nebula, and settled into its current state as a blue supergiant, all over the course of perhaps 6 to 8 million years. It will continue to burn for at least thousands more years, possibly much longer, before its core reaches the end of the nuclear fuel sequence and collapses. A human lifetime measured against this span is less than an instant. If the star's entire existence from formation to supernova were compressed into a single calendar year, a human life of 80 years would occupy roughly 4/10 of a second, less than a heartbeat, less than the blink of an eye. In that fraction of a cosmic instant, an individual human is born, learns to speak, goes to school, forms friendships, falls in love, builds a career, raises children, grows old, and dies. All of it happening in a duration so brief that on the star's timescale, it is essentially zero. And yet, in that blink, in that fraction of a cosmic moment, human beings have managed to do something that no star has ever done and no star ever will. We have understood. We have looked at the Hourglass Nebula through telescopes we invented and recognized it for what it is. We have measured the nitrogen enrichment and traced it back to nuclear reactions in the stellar core. We have calculated the mass of the nebula, the velocity of the expanding gas, the luminosity of the central star, the distance to the system. We have compared it to other stars that have already exploded and drawn conclusions about its probable future. We have done all of this from 7,200 light-years away, using light that left the star before the earliest civilizations on Earth, analyzed with instruments we invented in the last few centuries, interpreted with theories we developed in the last few decades. The universe does not know we exist. It has no awareness of the tiny patterns of matter on the surface of a small planet that have organized themselves into thinking things. The stars burn without knowing they are burning. The galaxies rotate without knowing they are rotating. The cosmic microwave background radiation, the afterglow of the Big Bang itself, fills all of space without the slightest awareness that it carries information about the origin of the universe. Everything happens according to the laws of physics, mechanically, predictably, without consciousness or purpose or meaning. And yet here we are, conscious, purposeful, meaning-seeking, looking at a dying star and feeling something, awe perhaps, or sadness, or wonder, or that peculiar mixture of all three that comes from contemplating our own smallness against the backdrop of something vast and ancient and utterly indifferent. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence, and in some strange, unsentimental way, that understanding is enough. Not enough to save us from the ultimate fate of all things, not enough to stop the stars from dying or the universe from expanding into cold emptiness, but enough to make our brief moment matter, enough to give it weight and texture and significance, enough to look at a dying star and feel, not just fear, not just curiosity, but kinship. We are made of the same stuff. We are participants in the same process, and for a little while we are the part of the process that knows what it is. Let us return now to the beginning, to the image, to the hourglass, 7,200 light-years from Earth, in the direction of the galactic center. A blue supergiant star sits at the center of a glowing structure of nitrogen-enriched gas and warm dust. The structure has the shape of an hourglass, two lobes extending in opposite directions from the star, pinched at the equator by a denser ring of material. The star that created this structure has a mass of 25 to 40 times that of the Sun. It radiates 300,000 times the Sun's luminosity. Its surface temperature is roughly 12,000 to 15,000 Kelvin, more than twice the temperature of our star's photosphere. It is losing mass at a rate of approximately 100,000th of a solar mass per year through a powerful stellar wind that streams outward at 200 kilometers per second. And at some point in the past, thousands of years ago, it convulsed violently enough to eject 1 to 2 solar masses of processed material into space, material that has been expanding outward ever since, cooling, condensing into dust, and glowing in the light of the star that cast it away. We have measured all of this. We have done it from across the galaxy, using telescopes that our species invented only a few centuries ago, and instruments that were inconceivable a few decades ago. We have spread the star's light into its component wavelengths and identified the elements in its atmosphere. We have imaged the nebula in visible light, in ultraviolet, in infrared. We have mapped the velocity structure of the expanding gas and determined its chemical composition. We have compared this star to others that have already died and concluded that it shares a disturbing resemblance to the progenitor of SN 1987A, the closest observed supernova in modern history. And we have built mathematical models that describe, in broad strokes, the sequence of events that will lead from this star's current state to its inevitable death as a core collapse supernova. But we have not answered the question that matters most. When? The honest answer is that we do not know. We cannot know, not with current technology, not with any technology we can presently conceive. The core of the star is hidden from us, sealed behind an opaque wall of hot plasma thousands of kilometers thick. The nuclear burning stages that will determine the timing of the collapse proceed deep inside, invisible to our instruments, on timescales that might be measured in hundreds of thousands of years, or might be measured in decades. The models that attempt to predict the outcome depend on parameters that are uncertain by factors that propagate through the calculations and amplify into qualitatively different endpoints. A slight change in the mass loss prescription shifts the final mass at collapse by several solar masses, which can mean the difference between a brilliant supernova and a quiet collapse into a black hole. A different treatment of convective overshooting changes the size of the burning shells, the duration of the advanced burning phases, and the structure of the iron core at the moment of collapse. We are not dealing with a system that is merely complex. We are dealing with a system in which the unknown inputs are large enough to alter the fundamental character of the output. This uncertainty is not a failure of science. It is a feature of the problem itself. Some systems in nature are predictable to extraordinary precision. The orbit of the moon can be calculated to within millimeters centuries in advance. The half-life of a radioactive isotope can be measured to 6 significant figures. The frequency of light emitted by a hydrogen atom is known to 1 part in a trillion. But the evolution of a massive star in its final stages is not one of these systems. It is a turbulent, non-linear, chaotic process involving the interaction of gravity, nuclear physics, fluid dynamics, radiation transport, neutrino physics, and magnetohydrodynamics across scales, ranging from the subatomic to the astronomical. The sensitivity to initial conditions and to poorly constrained physical processes means that deterministic prediction, in the sense of specifying the date and time of the collapse, is not merely difficult. It may be fundamentally impossible, and yet the science is not futile. Far from it. The study of HD 168,625 and stars like it has transformed our understanding of how the most massive stars live and die. It has revealed the mechanisms by which stars shed their outer layers, the chemical fingerprints of advanced nuclear burning, the physics of radiation-driven instabilities, the role of rotation and possible magnetic fields in shaping circumstellar environments, and the connection between pre-supernova evolution and the properties of the resulting explosion. Each observation, each model, each comparison to other stars adds another piece to a puzzle that is not yet complete but is far more detailed than it was even a decade ago. We may not be able to predict the moment of death, but we understand the process of dying with increasing depth and precision. There is something worth pausing over in the relationship between the star and the scientists who study it. The star does not know it is being observed. It burns because the laws of physics require it to burn. It sheds mass because the balance of radiation pressure and gravity dictates mass loss. It will collapse because the iron core will eventually exceed the Chandrasekhar mass, and the electron degeneracy pressure will fail. None of this requires a witness. The star will do what it does, whether or not any conscious being ever points a telescope at it, measures its spectrum, names it, catalogues it, or writes about it. The universe operates without an audience. It has been doing so for 13.8 billion years, and will continue to do so for trillions more. But we are here, and because we are here, the star is not just a physical object. It is also a subject of inquiry, a source of wonder, a challenge to our intellect, and a mirror in which we see our own limitations and our own extraordinary capabilities reflected back at us. We are the part of the universe that has learned to ask why. We are the atoms that have arranged themselves into patterns complex enough to study their own origins. And when we look at HD 168,625, we are looking at the forge in which atoms like ours were made. The nitrogen in the Hourglass nebula is the same element that constitutes 78% of the air we breathe. The carbon being fused in the stellar core is the same element that forms the backbone of every organic molecule in our bodies. We are not separate from this star. We are its distant relatives, its downstream products, the improbable consequences of a process that began with the death of earlier stars and will continue long after our own star has exhausted its fuel. The hourglass is running. We do not know how much sand remains. It might be a great deal, hundreds of thousands of years of quiet burning before the final stages begin. Or it might be very little, a few centuries, a few decades, an amount of time that overlaps with lives being lived today, with children being born this year, with futures being planned, and careers being built, and cities being constructed, on the assumption that the sky will look tomorrow much as it looks tonight. We do not know, and that not knowing is itself a kind of knowledge, a hard-won understanding of the limits of what can be determined from the outside of a system whose critical processes are forever hidden from view. What we can say is this: somewhere in the direction of Sagittarius, a star that outshines 300,000 suns is wrapped in a glowing cocoon of its own discarded material, shaped by physics into the form of an hourglass. The material is enriched with nitrogen, proof that the star's deep interior has been exposed. The star shares a detailed resemblance to another star that exploded in 1987, producing the most closely supernova in modern history. And when this star follows the same path, as it inevitably will, the event will be visible to the naked eye. A new light in the sky brighter than any star, persisting for weeks, slowly fading over months, and leaving behind an expanding cloud of debris containing the raw materials for future worlds. We are watching. We have instruments trained on the star and on the sky around it. We have neutrino detectors buried deep underground, in mines and beneath polar ice, waiting for the silent pulse of particles that will announce the collapse hours before the first photons arrive. We have gravitational wave detectors listening for the ripple in space-time. We have automated alert systems linking observatories on every continent into a coordinated response network. We are ready, or as ready as a species can be for an event that could occur at any moment or not for millennia. In the meantime, the star burns, the hourglass glows, the sand falls, and we, brief and small and astonishingly capable, continue to watch, to measure, to wonder, and to understand what we can of the vast, indifferent, magnificent process that made us and that will, in time, unmake us all.